Look up at the night sky. What do you see? Stars, planets, the gentle arc of the Milky Way. It's beautiful, humbling, and deeply familiar. But here's a secret. Almost everything that makes up our universe is completely invisible to us. In fact, 95% of the cosmos is composed of substances we can't see, touch, or even directly detect. Dark matter and dark energy. They don't emit light. They don't reflect it, yet they shape the fate of galaxies, steer the expansion of space itself, and hold the answers to questions we're only beginning to ask. We are living in a universe dominated by shadows, and the more we learn, the more we realize how much remains unknown. Despite centuries of scientific progress, from Galileo's first telescope to the profound insights of Einstein and Hubble, the cosmos is still brimming with mysteries that defy even the greatest minds. As Carl Sagan once beautifully said, "Somewhere, something incredible is waiting to be known." That sense of wonder, that thrilling promise of discovery, is what drives us to look deeper. And that's exactly what we're going to do together. In this video, we'll journey through 40 of the most fascinating unsolved cosmic puzzles and enigmas that range from the baffling behavior of black holes to the strange fine-tuning of the universe's birth. These aren't just gaps in knowledge, they're doorways. Each mystery invites us to rethink reality, to question our assumptions, and to imagine possibilities beyond our current understanding. What if everything we think we know about the universe is only a tiny fraction of the truth? From galactic anomalies and phantom energies to quantum conundrums and the haunting silence beyond our planet, we'll explore them all. This is more than a list. It's a mind-expanding expedition to the frontiers of ignorance, where the biggest questions lie. Whether you're a lifelong space enthusiast or someone who's simply curious about the nature of existence, there's a place for you here. So settle in, open your mind, and get ready to see the cosmos in a whole new light. The journey begins now. For as long as humans have gazed upward, we have been captivated by the grand spectacle of the night sky. Ancient astronomers across the globe, from the builders of Stonehenge to the Mayans, meticulously tracked the motions of the sun, moon, and stars. They solved practical mysteries, predicting the changing seasons, navigating vast oceans, and in doing so, they laid the very first stones on the path of cosmic inquiry. But with every answer came a new, more profound question. The patterns were clear, but what powered these celestial lamps? What were they made of? This cycle of discovery, where each solved puzzle reveals a deeper layer of mystery, is the entire story of astronomy. Consider the pivotal moment when Galileo first turned his telescope toward Jupiter in 1610. He saw 4 moons orbiting the giant planet, a stunning revelation that shattered the ancient belief that everything in the cosmos revolved around the Earth. It was a monumental solution to a centuries-old debate, yet it immediately posed new, more fundamental questions. If not everything circled Earth, what was the true arrangement of the solar system? What force governed the motions of these newfound worlds? This set the stage for Isaac Newton, who, with his laws of motion and universal gravitation, provided a magnificent framework that seemed to explain it all. For centuries, Newtonian mechanics was the ultimate tool, allowing us to predict planetary orbits and the paths of comets with breathtaking accuracy. It felt for a time like we had unlocked the universe's master clockwork, but the universe is never so easily tamed. In the early 20th century, small anomalies in Mercury's orbit and perplexing experiments with light refused to fit into Newton's elegant clockwork. The framework had cracks, and into those cracks stepped a visionary named Albert Einstein. His theories of relativity completely rewrote our concepts of space, time, and gravity. They solved the mystery of Mercury's wobble and predicted incredible things like the bending of starlight and the existence of black holes. Einstein himself understood that the drive to solve these puzzles is what propels us forward, famously noting that the most beautiful thing we can experience is the mysterious. Yet his own brilliant solutions unveiled an even more bizarre and counterintuitive reality. Relativity worked perfectly on the grand cosmic scale, but it was utterly incompatible with the other great pillar of modern physics, quantum mechanics, which ruled the subatomic world. This is the enduring pattern of scientific progress. Each new theory is a key that unlocks one door, only to reveal a hallway lined with many more, each leading to realms more strange and wonderful than the last. Our tools have evolved from naked eyes and stone circles to mighty instruments like the Hubble and James Webb Space Telescopes, which have peered back to the first galaxies, and massive particle colliders like the Large Hadron Collider, which smashes matter together to uncover its most fundamental secrets. Each technological leap has brought a revolution in understanding. Hubble's discovery of the expanding universe solved the mystery of the nebulae but unveiled the even bigger puzzles of the Big Bang and, eventually, dark energy. Today, we stand on the shoulders of all these giants, armed with tools of unimaginable power, and we are staring at a cosmos that is, in many ways, more mysterious than ever. The 40 puzzles we are about to explore are not a record of our failures. They are a map of the current frontiers of human knowledge. They represent the very latest set of doors that have swung open, inviting us to step through and see what lies beyond. This historical context is crucial. It teaches us that the greatest discoveries begin not with a shout of "Eureka," but with a curious, whispered, "That's funny." Imagine the grand spiral of a galaxy like our own Milky Way, a vast pinwheel of billions of stars all spinning together. According to the laws of gravity, the stars on the outer edges should be moving much more slowly than those near the dense center, just as Pluto orbits our Sun far more sluggishly than Mercury. But that's not what we see. For decades, astronomers have measured these rotation speeds and found something astonishing. Stars at the very outskirts of galaxies are whipping around just as fast as those near the core. It's as if the entire galaxy is embedded within an immense, invisible sphere of something massive, a hidden architecture whose gravity is the only thing preventing these stars from being flung off into the void. This is the first and perhaps most profound of our cosmic puzzles, the nature of dark matter, the universe's invisible architect. The story of this discovery begins not with a flash of light, but with a calculation of what was missing. In the 1930s, a brilliant and often contentious astronomer named Fritz Zwicky was studying the Coma Cluster, a huge gathering of galaxies millions of light years away. By measuring how fast these galaxies were moving relative to one another, he could estimate the cluster's total mass. But when he compared that to the mass he could actually see, all the stars and glowing gas, the numbers didn't just disagree, they were catastrophically different. The gravitational mass was hundreds of times greater. Zwicky concluded there had to be some form of dunkle materie, or dark matter, holding the cluster together. At the time, his idea was largely dismissed or ignored by the scientific community. It wasn't until the 1970s that the evidence became impossible to ignore, thanks to the meticulous work of astronomer Vera Rubin and her colleagues. While studying the rotation curves of individual spiral galaxies, she provided irrefutable proof that Zwicky was right. The stars in these galaxies were moving so fast that the gravity from the visible matter was utterly insufficient to hold them in orbit. Something else, something that neither emitted nor absorbed light, was providing the overwhelming majority of the gravitational glue. This wasn't just a curiosity in a distant cluster. It was a fundamental property of every galaxy we could study. So what is this mysterious substance? We know it exists because we can see its gravitational fingerprints everywhere, bending light from distant galaxies in a phenomenon called gravitational lensing, shaping the vast cosmic web of galaxy clusters and governing the very formation of structure in the early universe. Yet it remains utterly elusive. It doesn't interact with light or any part of the electromagnetic spectrum, and it seems to barely interact with normal matter at all, mostly just through the force of gravity. It's a ghost that we can only detect by watching how it moves the furniture around it. The leading theory is that dark matter is made of some kind of exotic particle that doesn't fit into our standard model of particle physics. For years, the prime candidate has been the WIMP, or weakly interacting massive particle. These hypothetical particles would be heavy and slow-moving, only interacting with normal matter through the weak nuclear force and gravity. Another compelling candidate is the Action, a particle originally proposed to solve a different quantum puzzle, which would be incredibly light but would exist in vast numbers. To find these phantoms, scientists have built incredibly sensitive experiments deep underground, like mine shafts in South Dakota or laboratories under mountains in Italy, hoping to catch the rare ping of a dark matter particle bumping into an atomic nucleus. Others are trying to create them in the high-energy collisions of the Large Hadron Collider. So far, after decades of searching, the detectors have remained silent. This profound lack of evidence forces us to ask a truly radical question. Is the problem that we haven't found the right particle yet, or could it be that our understanding of gravity itself is flawed on the largest scales? A minority of physicists propose theories like modified Newtonian dynamics, or MUND, which suggests that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies, eliminating the need for dark matter entirely. While MUND has had some success explaining galaxy rotations, it struggles to account for all the gravitational evidence we see in galaxy clusters and the early universe. The mystery, therefore, only deepens. We are left staring at the cosmos, knowing that over 80% of all matter is made of something completely alien to us, a substance that forms the hidden backbone of reality, yet slips through our nets every time we try to catch it. If dark matter is the invisible scaffolding holding the cosmos together, then its counterpart, dark energy, is the mysterious force actively pushing it apart. For most of the 20th century, astronomers were certain about one thing: the universe, born in the explosive fire of the Big Bang, had been expanding ever since. The only real question was whether that expansion would continue forever at a gradually slowing pace, or if the combined gravity of all the matter in the cosmos would eventually pull everything back together in a catastrophic big crunch. The answer, when it finally came, was so shocking and counterintuitive that it completely upended our understanding of cosmic fate. In 1998, two independent teams of astronomers were studying distant supernova exploding stars used as cosmic mile markers to measure how much the universe's expansion had slowed over time. To their absolute astonishment, they found it wasn't slowing down at all. It was speeding up. The universe's expansion is accelerating, as if some invisible repulsive force is overpowering gravity itself. This monumental discovery, which earned the teams the Nobel Prize in Physics in 2011, revealed the existence of dark energy. This isn't just a small component of the cosmos. Current measurements indicate that dark energy makes up a staggering 68% of the total energy density of the universe. It is the dominant force shaping the long-term destiny of everything. Think of it like this: gravity is the brake pedal on the universe's expansion, trying to pull things back together. But dark energy is the accelerator pressed firmly to the floor, pushing galaxies away from each other at an ever-increasing rate. And unlike matter or dark matter, which become diluted as the universe expands, dark energy appears to be a property of space itself. This means that as the universe gets bigger, there's actually more of this repulsive energy, leading to a feedback loop of faster and faster expansion. So what could it possibly be? The leading candidate is a concept that even Einstein himself toyed with and later called his biggest blunder, the cosmological constant. He originally introduced this constant into his equations of general relativity to describe a static, unchanging universe. When the expansion of the universe was later discovered, he discarded the idea. But now it's back with a vengeance. The cosmological constant suggests that empty space is not truly empty. It is seething with a uniform, constant energy that exerts a negative pressure, causing the expansion to accelerate. This energy is a fundamental property of the vacuum of space. The problem is when physicists try to calculate how strong this vacuum energy should be using quantum mechanics, their predictions are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the largest discrepancy between theory and observation in all of science. This absurdly large error has led scientists to explore other, more dynamic possibilities. Perhaps dark energy isn't constant. Maybe it's a force that changes over time, a concept sometimes called quintessence, named after the fifth element of ancient philosophy. Quintessence could be a new kind of energy field that permeates space but evolves, potentially weakening or strengthening as the cosmos ages. Figuring out which idea is correct, a steady cosmological constant or a changing quintessence, is one of the biggest goals in modern cosmology. To solve this, massive projects like the Dark Energy Survey on Earth and the incredible Euclid Space Telescope are creating incredibly detailed three-dimensional maps of millions of galaxies, tracing the history of the universe's expansion over billions of years to see exactly how the acceleration has changed. The implications of this discovery are truly existential, leading physicist Brian Greene to call dark energy perhaps the most profound mystery in all of science. If the acceleration continues unabated, driven by a constant or growing dark energy, it points toward a profoundly lonely and empty future. In a scenario cosmologists call the Big Freeze, the universe would expand forever, with galaxies flying apart so rapidly that the sky beyond our local group would eventually go completely dark. Stars would burn out and matter itself would decay, leaving a cold, dead, and nearly empty cosmos. But an even more dramatic and violent end is also possible: the Big Rip. If dark energy's repulsive force becomes stronger over time, it wouldn't just push galaxies apart. Billions of years from now, it could overcome the gravity holding individual galaxies together. Later, it could tear apart stars, then planets, and finally, in the last moments, rip apart atoms and the very fabric of spacetime itself. This isn't just a puzzle about the fate of the universe. It's a fundamental challenge to our core understanding of physics, forcing us to question the very nature of space, time, and the vacuum we once thought was nothing. Now, if dark energy is the mysterious force controlling the universe's ultimate fate, then we have to ask an even more fundamental question. How did the universe get its start in such a perfect, finely tuned way to allow for everything that followed? To answer that, we arrive at our third great cosmic puzzle, the mystery of cosmic inflation. Picture the very first moment after the Big Bang. The entire cosmos is smaller than a single atom, a seething, chaotic, and incredibly hot furnace. According to the standard Big Bang model, this tiny universe should have expanded, but at a more stately, predictable pace. That model, however, left cosmologists with some deeply confusing problems. The most famous of these is called the horizon problem. Imagine you light two candles on opposite sides of a very large, dark room. The light from one candle takes a certain amount of time to reach the other side. Now scale that up to the size of the universe. When we look at the cosmic microwave background, the ancient afterglow of the Big Bang, we see that it is almost perfectly uniform in temperature to within 1 part in 100,000. The problem is, the universe wasn't old enough at that time for light or heat or any form of information to have traveled from one side to the other to even out those temperatures. It's as if those two candles on opposite sides of a continent were somehow lit at exactly the same moment to the exact same brightness without ever having been in contact. How could regions of the universe that had never been connected, never exchanged a single photon, possibly know to be the same temperature? The standard Big Bang theory had no good answer. In 1980, a young physicist named Alan Guth provided a stunningly elegant solution. He proposed that in the first tiny fraction of a second of its existence, specifically from 10 to the power of -36 seconds to 10 to the power of -32 seconds, the universe didn't just expand. It underwent a period of hyper-exponential, faster-than-light expansion known as inflation. Think of it like this: if the universe was initially a marble, inflation would have blown it up to the size of our entire observable universe in less time than it takes for light to cross a single proton. This incredible growth spurt took all those tiny, connected regions of the early cosmos and stretched them out to become the vast, far-flung regions we see today, perfectly explaining why they all share the same properties. It solved the horizon problem in one brilliant stroke. This theory wasn't just a wild guess. It made specific, testable predictions. Most importantly, it predicted that the seeds of all future structure, the galaxies and clusters we see today, would have originated from microscopic quantum fluctuations that were stretched to astronomical sizes during inflation. These tiny ripples in spacetime would be imprinted as faint temperature variations in the cosmic microwave background. When satellites like COBE, WMAP, and most recently the Planck mission mapped the CMB with exquisite precision, that's exactly what they found. The pattern of hot and cold spots matches the predictions of inflation almost perfectly. It's a monumental success for the theory. Yet, for all its explanatory power, inflation remains one of the greatest unsolved puzzles because it raises profound new questions of its own. What was the engine that drove this incredible expansion? Physicists call it the inflaton field, a hypothetical field of energy that permeated the infant universe. We don't know what the inflaton is, what triggered it to kickstart inflation, or what made it eventually decay, converting its immense energy into the matter and radiation that filled the young cosmos. It's a mechanism we can describe mathematically, but its fundamental nature is a complete mystery. Furthermore, there are dozens of competing models of inflation, each with slightly different predictions. Some are simple, some are complex, and we currently lack the data to rule most of them out. The hunt for a smoking gun is ongoing. Many scientists believe the key evidence will be the detection of primordial gravitational waves, ripples in the fabric of spacetime generated by the violent energy of the inflationary expansion itself. These waves would leave a distinctive curling pattern, known as B-mode polarization, in the cosmic microwave background. Experiments like BICEP at the South Pole have been searching for this faint signal, but so far, interstellar dust has complicated the results. Finding those waves would be like hearing the faint echo of the Big Bang itself, confirming inflation beyond any doubt. This leads us to perhaps the most mind-bending implication of all. If inflation happened once, what's to stop it from happening again? Many versions of the theory suggest that inflation is not a one-time event but an eternal process. In this eternal inflation scenario, the inflattened field doesn't decay everywhere at once. Instead, our entire observable universe might be just one bubble that formed in a much vaster, eternally inflating multiverse. Beyond our cosmic horizon, an infinite number of other universes could be constantly bubbling into existence, each with its own unique laws of physics. Our entire reality, everything we know and are, could be a single bubble in a cosmic froth of universes. This puzzle doesn't just probe the origin of our universe. It forces us to confront the terrifying and magnificent possibility that our existence is just a small part of a far grander and perhaps infinite cosmic landscape. This brings us to a puzzle so profound it bridges the gap between physics and philosophy, questioning the very fact of our existence. We've explored the forces that shape the cosmos, but now we must ask, why is there a cosmos to shape at all? Why is there something rather than nothing? This is the essence of the fourth great cosmic mystery, the Baryon asymmetry problem. According to our best theories of the Big Bang and particle physics, the universe should have been born with absolutely equal amounts of matter and antimatter. Think of them as the ultimate cosmic twins, identical in mass but opposite in charge. For every electron, there should have been a positron, for every quark, an antiquark. And this creates a catastrophic problem because matter and antimatter are locked in a relationship of mutual annihilation. When a particle meets its antiparticle, they don't just cancel each other out, they explode into a flash of pure energy, leaving nothing behind. If the Big Bang had produced a perfectly symmetrical universe, all of those twin pairs would have immediately found each other in the searing heat of the early cosmos. Every single particle would have annihilated with its antiparticle, and the entire universe would have been left as nothing but a fading sea of light, a vast, empty expanse of radiation with no planets, no stars, no galaxies, and certainly no one to ponder its existence. Yet here we are. Our bodies, our world, every galaxy we see is made overwhelmingly of matter. Somehow, against all odds, a tiny, almost imperceptible surplus of matter survived that primordial annihilation. We are the descendants of that 1 in a billion imbalance, the leftover scraps from a near-perfect cancellation. So what tipped the scales? How did this crucial asymmetry come to be? Physicists have found one possible mechanism in a subtle phenomenon known as CP violation. The C stands for charge conjugation, which means swapping a particle for its antiparticle, and the P stands for parity, which is like looking at its mirror image. For a long time, we thought the laws of physics were perfectly symmetric under this combined CP operation. A left-handed particle should behave exactly like a right-handed antiparticle. But in 1964, experiments with strange particles called kaons showed this wasn't always true. There was a tiny 1 in 1,000 bias favoring matter over antimatter in their decays. This was a monumental discovery, proving that nature itself has a slight preference, a built-in arrow that can distinguish between matter and antimatter. It was so important it earned a Nobel Prize, but here's the catch. The amount of CP violation we've measured in the standard model of particle physics is nowhere near enough to account for the universe we see. The asymmetry in kaons and later in other particles like B mesons is a mere whisper of an effect. To create the overwhelming dominance of matter we live in, we would need a source of CP violation orders of magnitude stronger. The known effects are like a single drop of water when we need an entire ocean. This glaring shortfall is a clear sign that our current model of particle physics is incomplete. As the physicist Frank Close succinctly put it, the universe is made of matter, but we don't know why. This forces us to look beyond the standard model for answers. One compelling theory is leptogenesis. This elegant idea suggests that the asymmetry didn't start with the matter we're made of, the quarks and protons, but with their lighter cousins, the leptons, like neutrinos. The theory proposes that incredibly heavy, hypothetical neutrinos, which existed only in the first moments after the Big Bang, decayed in an asymmetrical way. As these heavy particles vanished, they could have produced a slight excess of ordinary matter neutrinos over antimatter neutrinos. Through a complex cascade of interactions and transformations, that initial lepton asymmetry could then have been converted into the Baryon asymmetry we see today, essentially seeding the entire visible universe from a neutrino imbalance. Other theories propose entirely new particles or forces that operated only at those unimaginably high energies of the very early universe, creating the conditions for a much more powerful matter-antimatter separation. The ongoing search for these answers drives experiments at the Large Hadron Collider and informs the design of next-generation particle detectors. The puzzle ultimately forces us to confront a deeply profound question. Was this life-giving imbalance simply a random statistical fluke, a quantum roll of the dice that just happened to go our way in one tiny pocket of a potentially vast multiverse? Or was it dictated by a fundamental, yet-to-be-discovered law of physics, a principle that makes a universe like ours not just possible but inevitable? We are here only because of a vanishingly small violation of a cosmic rule, a single winning ticket in the grandest lottery imaginable. Now, having grappled with the profound question of our own existence, we must turn our attention to a puzzle that strikes at the heart of why the universe is built the way it is. It's a problem of cosmic proportions, yet it plays out on the smallest of scales, and it's known as the hierarchy problem. To understand it, consider the forces that govern your daily life. When you use a simple refrigerator magnet, its tiny electromagnetic field can effortlessly defy the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons. That magnet, with a simple flick of your wrist, wins the tug of war against the gravity of a world. This isn't just a neat party trick, it's a demonstration of the most staggering imbalance in all of nature. The numbers are almost impossible to comprehend. The electromagnetic force is a staggering 10 to the power of 36 times stronger than gravity. That's a 1 followed by 36 zeros. To put that in perspective, if the strength of gravity were represented by the gentle weight of a single feather resting on your palm, then the electromagnetic force would be the raw, unleashed fury of 1,000 hurricanes all concentrated on that same spot. This isn't a minor difference, it's an abyss, an enormous gulf between the fundamental forces that shape our reality. And here is the puzzle. Why? Why is gravity so unimaginably feeble compared to its cosmic siblings? This isn't just a curiosity. For physicists, this hierarchy of force strengths is a screaming anomaly that points to a deep flaw in our understanding. The problem becomes especially acute when we try to merge our two great theories, the quantum world of the very small and the relativistic world of gravity. In quantum field theory, the properties of particles, including their mass, are constantly being influenced by a seething, temporary sea of virtual particles that pop in and out of existence. These quantum fluctuations should contribute enormous amounts to the mass of particles like the Higgs boson, which is responsible for giving other particles their mass. The calculations suggest the Higgs should be incredibly heavy, pulled up to the enormous energy scale where gravity becomes strong, a realm known as the Planck scale. To keep the Higgs mass at the relatively low value we actually observe, the theory requires an almost miraculous cancellation. the raw, unadjusted calculations and the necessary corrections would have to be fine-tuned to over 30 decimal places, a precision so absurd it's like balancing a pencil on its tip on the surface of the moon and having it still be standing a billion years later. To most physicists, this level of fine-tuning is not an explanation. It's a sign that we are missing a fundamental piece of the puzzle. One of the most elegant and celebrated proposed solutions is a concept known as supersymmetry. This beautiful theory posits that for every known particle in the Standard Model, every electron, quark, and photon, there exists a hidden super-partner particle. An electron would have a selectron, a quark would have a squark, and so on. These superpartners would have different spin properties but could cancel out the problematic quantum fluctuations that drive the Higgs mass so high. It would be a natural mathematical cancellation built into the fabric of the universe, eliminating the need for any miraculous fine-tuning. Supersymmetry wouldn't just solve the hierarchy problem. It would also provide a perfect candidate for dark matter and offer a crucial step toward unifying all the fundamental forces. For decades, it was the darling of theoretical physics. Yet, the universe has a habit of dashing our most elegant ideas. The Large Hadron Collider, our most powerful microscope for probing these high-energy realms, was widely expected to discover this menagerie of super-partner particles. But after years of smashing protons together and sifting through the debris, the detectors have remained silent. No selectrons, no squarks, no photinos. We have found nothing but empty space where supersymmetry predicted new physics should be. The particles, if they exist at all, must be far heavier than the theory initially hoped, which in itself diminishes their ability to neatly solve the original problem. This non-discovery is arguably more profound than a discovery would have been. It has forced a deep and uncomfortable rethink, deepening the mystery of the hierarchy rather than resolving it. This failure has given renewed energy to other, even more radical ideas. Perhaps the problem isn't with the particles, but with gravity itself. Theories involving extra dimensions of space propose that the force of gravity only appears weak to us because it is not confined to our familiar 3 dimensions of space. It could be leaking out or diluting into these other hidden dimensions. In this scenario, gravity is just as strong as the other forces, but its strength is spread so thin across the full bulk of higher dimensional space that only a tiny, feeble trickle of it is left for us to experience in our 3-dimensional world. It's like trying to feel the full pressure of a fire hose by only touching a single, thread-like stream of water shooting out from it. This incredible idea is testable in principle. If these extra dimensions exist, the Large Hadron Collider might someday create microscopic black holes or detect particles disappearing into them, offering a glimpse into a truly multidimensional cosmos. The hierarchy problem, then, is far more than a technical issue with a calculation. It is a direct challenge to the completeness of our physical models. The glaring weakness of gravity is a clue, a cosmic signpost pointing toward physics beyond our current understanding. It forces us to ask whether we have been thinking about gravity all wrong. Could it be an emergent phenomenon, not a fundamental force, arising from the collective behavior of something else entirely, like the way temperature emerges from the motion of atoms? Or does its unique nature mean it can never be fully integrated with the quantum world in the way we have hoped? This puzzle reminds us that even the most familiar force, the one that grounds us to our planet and guides the planets in their orbits, holds profound and unresolved secrets about the true architecture of the universe. After exploring the staggering imbalances of forces and matter that define our universe, we turn to what should be the most pristine and reliable piece of evidence we have, the cosmic microwave background. Think of it as the universe's very first baby picture, taken when it was a mere 380,000 years old. Before that moment, the cosmos was a seething, opaque plasma, too hot and dense for light to travel freely. As it finally expanded and cooled enough for atoms to form, the first photons were set free, and they have been traveling across the void ever since. Today, that ancient light arrives at our telescopes as a faint, cold whisper of microwave radiation, bathing the entire sky in a nearly uniform glow. This CMB is the crown jewel of modern cosmology, a stunning confirmation of the Big Bang model, and its overall uniformity tells a story of a universe that was once incredibly hot and dense. But just like a family photo that reveals a strange, unexplained shadow in the corner upon closer inspection, this baby picture contains subtle, perplexing anomalies that have astronomers scratching their heads. The standard cosmological model, which includes dark matter and dark energy, predicts a very specific pattern for this remnant radiation. It should be almost perfectly smooth, with only tiny, random fluctuations in temperature about 1 part in 100,000. That served as the seeds for all the galaxies and clusters we see today. And for the most part, that's exactly what we see. Satellites like NASA's WMAP and the European Space Agency's Planck have mapped this radiation with breathtaking precision, creating a mottled map of the entire sky that largely validates our entire understanding of cosmic evolution. But when scientists scrutinized these maps with incredibly sophisticated statistical tools, they found features that are, in a word, weird. The universe's baby picture has strange quirks that the standard model simply cannot explain. Perhaps the most famous of these is the so-called axis of evil. This isn't a name from a science fiction movie. It's a term cosmologists use with a mix of humor and genuine concern. It refers to the puzzling discovery that some of the largest fluctuations in the CMB appear to be aligned with the plane of our own solar system. This is deeply troubling because it violates a fundamental principle of modern cosmology, the cosmological principle. This principle states that the universe on very large scales should be isotropic and homogeneous. It should look the same in every direction and have no preferred center or axis. Finding that the universe's largest structures seem to be oriented in a way that's related to our own local neighborhood is like discovering that every continent on Earth is mysteriously aligned with the location of your backyard. It suggests that either we are, against all odds, at a special place in the universe, which is a notion science has fought against for centuries, or there is something fundamentally incomplete about our models. Then there are the unexpected cold spots. One in particular, located in the constellation Eridanus, is colossal, stretching over 1 billion light-years across, and is significantly colder than the surrounding areas. While the CMB is filled with hot and cold spots, this one is a dramatic outlier. The most straightforward explanation would be that it's a giant supervoid, an immense region of space with far fewer galaxies and less matter. As light travels through such a void, it can lose a tiny amount of energy, creating a slightly colder spot in the CMB. But when astronomers went looking for this proposed void, they couldn't find one nearly large enough or empty enough to account for the dramatic temperature drop. The observed cold spot is simply too big and too cold to be easily explained by a lack of galaxies. The Planck satellite, our most advanced instrument for studying the CMB, didn't resolve these mysteries, it confirmed them. The data from Planck is exquisitely precise, and it reinforced the existence of these anomalies. The team behind the mission ran exhaustive tests to see if the strange alignments or the cold spot could be mere statistical flukes, artifacts of how we process the data, or even subtle errors in the instrument itself. After years of analysis, the consensus is that these features are real. they are genuinely imprinted on the fabric of the cosmos, and we have no definitive explanation for them. This leaves us with two radically different possibilities. The first, and more conservative, is that we are simply seeing a cosmic coincidence. In a universe that is inherently random on some level, even a perfectly isotropic cosmos could, by sheer chance, produce a few patterns that look strangely aligned to us. We might just be the unlucky observers who happen to see a statistical anomaly on a grand scale. The second possibility is far more thrilling. These quirks could be the first faint cracks in the standard model, tiny windows into new physics that operates on scales we can barely imagine. Perhaps the axis of evil is a fossil imprint from a time before the Big Bang, a remnant of some exotic physics that set the initial conditions for inflation. Maybe the cold spot is evidence of a collision with another universe in the vast multiverse, a cosmic bruise left from a long-ago encounter with a reality beyond our own. These anomalies force us to ask an unsettling question. Is our universe's baby picture incomplete? Are we missing a crucial part of the story, a hidden chapter that explains these strange features and reveals a cosmos far more complex and interconnected than we ever dared to dream? Knowing that our universe's infancy holds such puzzling features only makes the question of its ultimate fate feel even more pressing and profound. We have peered back to the very beginning, but now we must cast our gaze forward across trillions of years to confront the seventh great cosmic puzzle. How will it all end? The destiny of everything, every star, every planet, every atom hangs in the balance, and the answer depends entirely on the mysterious properties of dark energy, a force we are only beginning to comprehend. Cosmologists have outlined several dramatic, almost poetic scenarios for the cosmos's final act, each more awe-inspiring and terrifying than the last. The most widely accepted model, based on our current best measurements, is known as the heat death or the Big Freeze. In this distant future, the relentless acceleration driven by dark energy continues to push galaxies apart at an ever-increasing rate. Eventually, all stars will burn out, their fuel exhausted. Galaxies beyond our local group will fade from view, their light stretched by expansion into undetectable wavelengths until the entire sky beyond our immediate neighborhood goes completely and utterly black. Over incomprehensible timescales, even the most stable matter will begin to decay. Protons themselves might evaporate. The universe will become a vast, cold, and infinitely dilute sea of isolated particles and radiation, where the temperature approaches absolute zero and no energy gradient remains to power any process, any thought, any change. It is the ultimate thermodynamic equilibrium, a quiet, dark, and eternal silence. This is not an explosive end, but a slow, inexorable fading into nothingness. But what if dark energy is not as gentle as the cosmological constant suggests? A more violent alternative is the Big Rip. This scenario arises if the repulsive force of dark energy doesn't just remain constant, but actually grows stronger over time, becoming more powerful as the universe expands. For billions of years, the effect would be subtle, but eventually, this phantom dark energy would overcome the gravitational glue holding galaxy clusters together. Later, it would tear individual galaxies apart. As the force intensifies, it would pull stars from their solar systems, and then planets from their stars. In the final moments, just before the end of time itself, the repulsive force would become so strong that it would overcome the forces holding atoms together. Molecules, then atoms, and finally atomic nuclei would be violently ripped apart, shredding the very fabric of spacetime. The universe would end not with a whimper, but with a catastrophic, instantaneous tear. There is a third, more classical possibility, the Big Crunch. This was the favored outcome for much of the 20th century before the discovery of dark energy. It imagines a universe where the collective gravity of all matter eventually halts and reverses the expansion. Galaxies would begin to rush back toward each other, their light blue-shifting as space contracts. The temperature of the cosmos would rise, and the sky would grow hotter and brighter. Eventually, all matter and energy would be compressed back into an infinitesimally small, infinitely hot and dense state, a singularity mirroring the Big Bang itself. For some, this cyclical vision is appealing, as it opens the door to theories of an oscillating or cyclic universe, where a new Big Bang follows the crunch in an endless cycle of cosmic death and rebirth. The critical factor that decides between these fates is the nature of dark energy, specifically a property known as its equation of state parameter, represented by the letter W. If W is exactly -1, it signifies a constant dark energy leading to the big freeze. If W is less than -1, we are headed for a big rip. And if dark energy were to somehow decay away, allowing gravity to dominate, a big crunch could still be on the table. The problem is, we have no idea what W truly is or if it might change over time. Our measurements are still too imprecise to rule out any of these terrifying possibilities. This uncertainty is compounded by another major puzzle we discussed earlier, the Hubble tension. The fact that we get different values for the universe's expansion rate depending on whether we look at the early universe or the nearby universe suggests that our models of cosmic evolution might be missing a crucial ingredient. This discrepancy doesn't just affect our understanding of the past, it throws the entire future into question. If we can't even agree on how fast the universe is expanding now, how can we possibly predict its ultimate fate with any confidence? It's a humbling reminder, perfectly captured by astrophysicist Neil deGrasse Tyson's observation that the universe is under no obligation to make sense to you. This forces us to confront the most profound questions of all. Are we living in a universe destined for a permanent, irreversible death, a frozen eternity of nothingness? Or could our cosmos be part of a grand, cyclical process of destruction and creation, an infinite loop where each ending is merely a prelude to a new beginning? The answer lies hidden in the elusive nature of dark energy, a mystery that represents one of the final frontiers of cosmology. To solve the puzzle of how the universe will end, we must first unravel the secrets of the invisible force that controls its expansion, a quest that pushes the very limits of human understanding and reminds us that the story of the cosmos is still being written. From the vast, cold fate of the cosmos, we now plunge into a realm where reality itself becomes fluid and uncertain, a domain where the very act of looking at something can change its fundamental nature. This is the bizarre world of quantum mechanics, and at its heart lies our eighth great cosmic puzzle, the measurement problem. To grasp its strangeness, consider one of the most famous thought experiments in all of science, Schrödinger's cat. Imagine a cat sealed inside a box with a diabolical device, a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter triggers the hammer to smash the vial, killing the cat. According to the bizarre rules of quantum mechanics, that radioactive atom exists in a state of superposition before we look. It is both decayed and not decayed at the same time. And since the fate of the cat is tied to the atom, the cat itself must also be in a superposition, both alive and dead, until the moment the box is opened and someone peers inside. This isn't a statement about the well-being of felines. It's a profound paradox designed to illustrate a terrifying implication of the theory. How can reality be in two contradictory states at once? And what magical power does a simple observation have to force it to choose just one? The prevailing explanation for decades has been the Copenhagen interpretation, championed by figures like Niels Bohr and Werner Heisenberg. It proposes that a particle, like an electron, doesn't have a definite position or state until it is measured. Instead, it is described by a wave function, a mathematical cloud of probability representing all the possible places it could be or states it could be in. This wave function evolves smoothly and predictably over time, following the Schrödinger equation. But the instant a measurement is made, something truly inexplicable happens. The wave function collapses. All those shimmering possibilities instantly vanish, and the particle snaps into a single, definite reality. The problem, the deep and unresolved puzzle, is that the theory provides no mechanism for how or why this collapse occurs. What exactly qualifies as a measurement? Is it the interaction with a measuring device, a human eye, a conscious mind? The mathematics offers no answer. It simply postulates that observation creates reality, a concept that feels more like philosophy than physics. Dissatisfaction with this magical seeming collapse has led to a spectrum of alternative interpretations, each more mind-bending than the last. Perhaps the most audacious is the many worlds interpretation. Proposed by Hugh Everett in the 1950s, it eliminates the collapse entirely. It suggests that the wave function never collapses. Instead, at the moment of every quantum decision, like whether that atom decayed or not, the universe literally splits into multiple branches. In one universe, you open the box and find a living cat relieved. In another, equally real universe, an identical version of you opens the box and finds a dead cat, horrified. There is no single outcome. Every possible outcome happens in its own parallel world. This interpretation is elegant because it does away with the fuzzy concept of measurement, but it does so at the staggering cost of proposing an infinite and ever-branching multiverse of realities, most of which we are forever unaware of. Other interpretations take a completely different tack. David Bohm's pilot wave theory, for instance, suggests that particles are indeed real objects with definite positions at all times, but they are guided by a hidden pilot wave that dictates their motion. This explains quantum weirdness without superposition or collapse, but it requires influences that seem to defy local causality. Then there are objective collapse models, which propose that wave function collapse is a real physical process that happens spontaneously when a system becomes too large or too complex, perhaps due to some undiscovered link between quantum mechanics and gravity. These theories predict tiny deviations from standard quantum predictions that experiments are only now becoming sensitive enough to test. And then there are the experiments themselves, which continue to deepen the mystery. The quantum eraser experiment, for instance, seems to show that measurements made in the present can retroactively change the past behavior of a particle, challenging our most basic intuition about cause and effect. All of this forces us to confront a question that straddles the line between science and metaphysics. What is the role of consciousness? If a measurement is what defines reality, does that require a conscious observer to be present? Some interpretations, though highly controversial, have suggested that consciousness itself is the fundamental ingredient that collapses the wave function, placing the human mind back at the center of the universe in a way not seen since the days before Copernicus. Most physicists find this idea deeply unsatisfying, preferring to believe that reality exists independently of whether anyone is looking. But the alternative is to accept that the universe is fundamentally probabilistic, that at its base there is no certain reality, only a set of potentialities and chances. The measurement problem is more than a technical issue in physics. It is a direct challenge to our understanding of existence. It blurs the line between the observer and the observed, forcing us to ask if we can ever truly be separate from the reality we are trying to measure, or if our attempts to understand the universe are an inseparable part of its unfolding story. If the measurement problem makes reality feel uncertain and observer-dependent, then the next puzzle makes the universe feel deeply, mysteriously connected in a way that defies all conventional intuition. Albert Einstein, for all his revolutionary brilliance, found one consequence of quantum theory so disturbing that he famously dismissed it as spooky action at a distance. He was referring to the bizarre phenomenon of quantum entanglement, a concept so strange it seems ripped from the pages of science fiction. Imagine you have a pair of magical dice. You take them to opposite ends of the galaxy, and the moment you roll one here and see it land on a 3, you know instantly, with 100% certainty, that the die 10,000 light-years away has also landed on a 3. This isn't just a prediction, it's a direct, instantaneous connection. In the quantum world, this is exactly what happens with entangled particles, like pairs of electrons or photons. They are created or interact in such a way that their properties, say, their spin or polarization, become perfectly correlated. They form a single, unified quantum system, no matter how far apart they are dragged. For decades, this was treated as a philosophical curiosity, a weird mathematical quirk in the equations that surely couldn't reflect reality. Einstein and others argued that there must be some hidden variables, some predetermined classical property we just couldn't see that would explain the correlation without any spooky instant communication. They believed the universe was locally real, meaning objects are only influenced by their immediate surroundings and have definite properties whether we measure them or not. But in the 1960s, a brilliant Irish physicist named John Bell devised a way to test this idea. He created a mathematical theorem, Bell's inequality, that could distinguish between a universe with hidden local variables and one with true quantum weirdness. The experiments, first conducted decisively by Elaine Aspect and others in the 1980s, came down resoundingly on the side of weirdness. They proved that entangled particles do indeed influence each other's states instantly, with the correlation happening faster than any signal could travel between them at the speed of light. As Bell himself put it, the results showed that what is proved by impossibility proofs is lack of imagination. The universe was far more imaginative than anyone had dreamed. This confirmation of non-locality, that two things can be connected across vast distances without any physical force or signal mediating that connection, creates a direct tension with Einstein's theory of relativity, which establishes the speed of light as the universe's ultimate speed limit. Nothing, not even information, can travel faster than light. So how do entangled particles manage it? The key to resolving the paradox, and a point that is often misunderstood, is that this instantaneous change cannot be used to send a meaningful, faster-than-light message. While measuring one particle immediately sets the state of its entangled partner, the outcome of your own measurement is completely random. You have no control over whether you get a spin-up or spin-down electron. You only know that your distant colleague will get the opposite. The person receiving the other particle just sees a random result. It's only when you later get together and compare your lists of results via a slow, classical channel like a telephone call that you see the perfect, spooky correlation. So, while the connection is instantaneous, it cannot be used for superluminal communication. The universe, it seems, prevents time travel and paradoxes through a clever loophole of randomness. But this only deepens the mystery. If information isn't traveling, what is happening? What is the nature of this connection? Modern physics is grappling with explanations that are as profound as the phenomenon itself. Some theories within the framework of quantum mechanics suggest that we have to let go of our classical notion that particles are separate, distinct objects. At a fundamental level, perhaps they are not. Entanglement might be revealing that the universe is fundamentally interconnected, that separation is an illusion born from our limited perception. More radical theories, like the holographic principle, propose that our three-dimensional reality, including the space that separates particles, is actually a projection from a two-dimensional surface where distance has no meaning. In this view, two entangled particles aren't communicating across a vast gap. They are essentially adjacent in the deeper, real fabric of the cosmos. String theory, too, offers pathways for such connections through higher dimensions. This leads to a breathtaking possibility, one that completely overturns our everyday experience of the world. Could it be that space itself is not a fundamental stage upon which the drama of physics plays out, but an emergent property? Perhaps what we perceive as empty space and vast distances is something that crystallizes out of a more basic, underlying network of quantum connections. In this view, entanglement isn't happening through space. It is what creates the very notion of space and proximity. The universe might be better thought of as a vast web of correlations, where the strength of entanglement defines the distance between points. This isn't just philosophical speculation. It's an active area of research at the frontiers of theoretical physics, trying to build space-time itself from the bottom up out of quantum bits. The eerie phenomenon of quantum entanglement, once dismissed as a ghost in the machine, might actually be the fundamental thread from which the entire tapestry of reality is woven, suggesting a cosmos far more deeply and wonderfully interconnected than we ever imagined. Stephen Hawking's most revolutionary idea wasn't about how black holes work, but about how they die. In 1974, he made a shocking prediction that sent shockwaves through the world of physics. He calculated that black holes aren't completely black after all. Due to weird quantum effects happening right at the very edge of the event horizon, they should slowly leak a faint glow of radiation, now famously known as Hawking radiation. This process isn't fast. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate, but it is relentless. Over immense eons, a black hole will lose mass, shrink, and eventually, according to Hawking's original math, vanish completely in a final puff of radiation. This was a beautiful, elegant idea that married quantum theory with gravity, but it came with a terrifying and, for many physicists, unacceptable price: the complete and utter destruction of information. What does that mean? In our everyday world, information is just another word for history. If you burn a book, it seems destroyed, but in principle, if you could collect every single smoke particle, every bit of ash, and trace the exact heat energy released, you could reconstruct the book perfectly. The information about what was written on those pages is never truly lost. It's just scrambled. Quantum mechanics elevates this idea to a fundamental law of the universe, the principle of unitarity. It states that information is always preserved. The universe at its heart is predictable. If you know the exact quantum state of everything right now, the laws of physics should, in theory, allow you to calculate everything about the past and the future. It's the ultimate cosmic ledger, and its balance must always be maintained. But Hawking's calculations suggested that black holes are the ultimate arsonists. When something falls into a black hole, a book, a star, an entire spaceship, all the information about what those things were made of, their shape, their history, is irretrievably lost behind the event horizon. Then, when the black hole itself evaporates, all it gives back is a bland, random, and featureless thermal glow. That final burst of Hawking radiation would be exactly the same whether the black hole was made from collapsed stars or compressed copies of the complete works of Shakespeare. The information is not just scrambled, it is seemingly erased from existence. This is the black hole information paradox, and it suggests that the universe's most fundamental accounting system is fundamentally broken. For decades, this was the uncomfortable stalemate. Physicists had to choose their poison. Either quantum mechanics was wrong and information could be destroyed, or general relativity was wrong and our understanding of black holes was deeply flawed. Hawking himself famously bet other physicists that information was indeed lost, a bet he eventually conceded in 2004. But conceding the bet didn't solve the paradox, it just acknowledged that a solution must exist. The search for that solution led to an even more frightening idea, the firewall paradox. If information is to be saved, then something dramatic must happen at the event horizon to encode the data of infalling objects into the outgoing Hawking radiation. This process, however, would require an incredibly energetic transformation right at the point of no return. The calculations suggested that the empty space just outside the event horizon, which Einstein's relativity says should be smooth and uneventful for an astronaut falling in, would instead be a searing wall of ultra-high-energy particles, a firewall that would instantly incinerate anything crossing it. So now the paradox is even worse. We either have to accept that information is lost, violating quantum mechanics, or we have to accept that the event horizon is a deadly firewall, violating relativity's central tenet that free fall should feel like floating in empty space. It's a brutal clash between our two most successful theories of reality, and it highlights the desperate need for a theory of quantum gravity to resolve the conflict. The most promising resolution to this decades-long puzzle comes from a concept that sounds like it's straight out of science fiction: holography. Proposed by physicists like Gerard T. Hooft and Leonard Susskind, the holographic principle suggests that all the information that falls into a black hole isn't lost inside its three-dimensional volume. Instead, it is perfectly encoded and preserved on its two-dimensional surface, the event horizon. Imagine the surface of the black hole is like the film in a hologram. A hologram is a two-dimensional piece of plastic, but when you shine a laser through it, it projects a full three-dimensional image. In the same way, the holographic principle suggests that the entire three-dimensional interior of the black hole, including all the stuff that fell in, is actually a projection from the information painted on its two-dimensional surface. The information never actually travels inward past the point of no return. It is smeared across the horizon and then slowly radiated back out in the Hawking radiation in an incredibly complex but perfectly recoverable code. This means the astronaut falling in might not hit a firewall, but from the perspective of the information itself, it never enters a mysterious singularity. More recently, an even more sophisticated idea has emerged from the complex mathematics of gravitational path integrals called the island theory. It suggests that as a black hole evaporates, regions in its interior, dubbed islands, become mathematically connected to the radiation far outside. These islands effectively become part of the external universe's information storage system. The information about what fell in isn't on the surface or in the center. It's in a weird quantum connection between the radiation we can collect and a region deep inside the black hole itself. This bizarre idea provides a specific mechanism for how information can escape without violating any laws, and it's currently at the absolute cutting edge of theoretical physics. The implications of this puzzle are far more than just academic. If information can be lost, it strikes at the very heart of scientific determinism. It would mean the universe is fundamentally unpredictable and that the past is not fixed. We could never be sure about the history of an object that emerged from a black hole's evaporation. The very foundation of cause and effect would be called into question. Resolving the information paradox is therefore about more than just understanding black holes. It is about determining whether the universe operates by logical, predictable rules from its beginning to its end. It represents the final battlefield where general relativity and quantum mechanics must either find a peaceful union or one must emerge victorious, forever changing our comprehension of reality itself. While our most powerful particle accelerators on Earth, like the Large Hadron Collider, can hurl protons to incredible energies, they are utterly dwarfed by the natural particle cannons operating in the depths of space. From the void, our planet is constantly bombarded by a rain of atomic fragments known as cosmic rays. Most are low-energy protons, but a tiny fraction are something else entirely: ultra-high-energy cosmic rays. These are single subatomic particles, often bare atomic nuclei, that carry kinetic energy equivalent to a well-thrown baseball, all compressed into a speck smaller than an atom. They are the universe's fastest, most energetic particles, moving at a staggering 99.9999999% of the speed of light, and their existence presents us with our 11th great cosmic puzzle. What natural particle accelerator in the cosmos could possibly be this powerful? The sheer energy these particles pack is almost beyond comprehension. The most extreme examples have been measured at over 100 electron-volts. To put that in perspective, that's millions of times more energy than the protons colliding inside the Large Hadron Collider, and about 40 million times the energy of the protons accelerated in medical cancer treatment. This isn't just a record-breaking number, it's a fundamental challenge to physics. According to a principle known as the GZK cutoff, proposed by Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, particles with such immense energy should not be able to travel very far through the cosmos. They should constantly bump into the low-energy photons of the cosmic microwave background, the leftover radiation from the Big Bang, losing energy with every collision until they drop below this theoretical limit. The fact that we detect them at all means they must come from relatively nearby sources within our local supercluster of galaxies, perhaps within 200 million light-years or so. Yet, when we look out into that region of space, we cannot find anything obvious that is capable of this feat. This isn't just an academic curiosity. These particles are a tangible, if rare, presence. They strike our atmosphere with enough force to create massive air showers, cascades of billions of secondary particles that spread out over kilometers as they rain down to the surface. While our atmosphere protects us from their direct effects, they pose a genuine risk to astronauts on long-duration spaceflight, potentially damaging DNA and sensitive electronics on satellites. Pinpointing their origin is a matter of both profound curiosity and practical necessity. The hunt for these cosmic accelerators has led scientists to some of the most violent and energetic objects in the known universe. The prime suspects are active galactic nuclei, the incredibly luminous cores of galaxies powered by supermassive black holes actively consuming vast amounts of matter. The intense magnetic fields and relativistic jets shooting out from these monsters could, in theory, accelerate particles to these unbelievable energies. Other candidates include the cataclysmic deaths of massive stars in supernova explosions or the even more powerful gamma-ray bursts, the most energetic explosions since the Big Bang itself, which could provide a brief but unimaginably powerful kick to charged particles. However, for all their might, none of these spectacular candidates perfectly fits the bill. When astronomers trace the arrival directions of these ultra-high-energy cosmic rays back to their potential sources, they don't find a neat pattern pointing to a known active galaxy or a recent gamma-ray burst. The map is frustratingly diffuse. This is partly because these particles are not like photons of light that travel in straight lines. They are charged, meaning their paths are bent and twisted by the magnetic fields that permeate the interstellar and intergalactic medium. It's like trying to find the source of a downpour by looking at the ripples in a river. The original direction has been hopelessly scrambled. Massive international collaborations like the Pierre Auger Observatory in Argentina, a detector array that covers an area of 3,000 square kilometers, the size of Rhode Island, are dedicated to catching these rare events and triangulating their origins. They have made progress finding a weak correlation with the distribution of nearby matter, but a definitive smoking gun source has remained elusive. This persistent failure to find a conventional explanation has opened the door to some truly exotic possibilities. Could these particles be the telltale signature of physics beyond the standard model? One thrilling idea is that they are not accelerated at all, but are instead the decay products of something far more mysterious. Hypothetical super-heavy dark matter particles, relics from the very early universe with masses far beyond any known particle, could be decaying in the halo of our own galaxy, spraying out ultra-high-energy protons and nuclei as their final signature. Alternatively, they could be evidence of cosmic defects in the fabric of spacetime itself. Theories suggest that as the early universe cooled and underwent phase transitions, topological defects like cosmic strings or magnetic monopoles could have formed. The immense energy density stored in these ancient flaws could be released in violent bursts, creating the very particles we detect. These ideas are highly speculative, but they illustrate a critical point. The mystery of ultra-high-energy cosmic rays is more than just an astronomical treasure hunt. It is a fundamental probe into the most extreme physical processes the universe can concoct, a reminder that there are forces at work in the darkness that we have not yet begun to comprehend, capable of hurling fragments of atoms across millions of light years with energies that defy our best theories and our most powerful machines. We often think of our home galaxy, the Milky Way, as a grand island universe majestically spinning in the void, but this is an illusion of perspective. In reality, our galaxy is not adrift. It is caught in a powerful, unseen current, pulled by gravitational forces we are only beginning to map. Our entire local group of galaxies, including the Great Andromeda, is rushing through space at a breathtaking 600 kilometers per second toward a specific point in the constellation Centaurus. For decades, the source of this immense pull was one of the most frustrating puzzles in astronomy because it seemed to be located directly behind the core of our own galaxy, in a region astronomers call the zone of avoidance. This isn't a place of danger, but of simple obstruction. The central bulge of the Milky Way is packed with stars, gas, and immense clouds of cosmic dust that block our view in visible light, creating a blind spot that covers a significant portion of the southern sky and hiding whatever was tugging on us from view. This mysterious, hidden gravitational powerhouse was dubbed the Great Attractor. Its influence isn't limited to just us. It's pulling in hundreds of thousands of galaxies across our local universe. The sheer scale of the force required to move entire galaxies like ours suggested something truly colossal, a concentration of mass that could be 100,000 times more massive than the Milky Way. Initial theories proposed it was a massive supercluster of galaxies, a dense knot in the cosmic web whose gravity was drawing everything in its vicinity toward a common center of mass. But without being able to see it, the Great Attractor remained a ghost, a gravitational anomaly inferred from motion but not directly observed. It was a classic cosmic detective story. We could see the effect, but the culprit was hiding in plain sight, obscured by the dusty veil of our own galactic backyard. The key to piercing this veil was to look with different eyes. Visible light was useless, but infrared and radio waves can pass through the obscuring dust. As technology advanced, astronomers began to conduct vast surveys using these wavelengths, and slowly, the hidden architecture of our cosmic neighborhood began to emerge. What they found was not a single, monstrous object, but something far more grand and complex. The great attractor appears to be the gravitational core of an immense supercluster of galaxies, the heart of a structure so vast it redefines our address in the universe. In 2014, a team led by astronomer R. Brent Tully used the motions of thousands of galaxies to map this structure in unprecedented detail, revealing a cosmic continent they named Laniakea, the Hawaiian word for immeasurable heaven. Laniakea is not just a cluster, it is a supercluster, a vast filamentary network of over 100,000 galaxies stretching across 500 million light-years. Our Milky Way is not even at its center. We are out in the suburbs on a distant tendril, flowing along with the cosmic current toward the gravitational center of this immense structure, which lies near the Norma cluster. As Tully so poetically described it, we are part of a river of galaxies flowing toward a common destination. This mapping was a monumental achievement, providing a stunning new context for our place in the cosmos and seemingly solving the mystery of what was pulling us. The great attractor was no longer a singular, hidden monster, but the dense central valley of our local supercluster. Yet, even with this breathtaking discovery, the puzzle is not fully solved. The precise mass distribution within Laniakea, and whether it fully accounts for the peculiar motion of our galaxy and its neighbors, is still a subject of active research. Some studies suggest that there might be even more to the story, that the pull we feel could be influenced by structures beyond Laniakea, like the immense Shapley supercluster, which lies hundreds of millions of light-years further away and is the largest known concentration of matter in our local universe. This raises a profound question. Is the great attractor a typical, if massive, concentration of galaxies within the predictable web of cosmic structure, or does its specific pull hint at something more unusual, a density in the universe that is even greater than our models anticipate? The effort to completely unravel this mystery continues, a powerful reminder that some of the greatest cosmic secrets are not found in the far reaches of the observable universe, but right in our own celestial backyard, hidden behind a curtain of stars. Yet for all its immensity and ancient age, the cosmos presents us with a profound and unsettling silence. After contemplating the invisible forces that shape galaxies and the strange currents that pull them through the void, we are left with a question so simple a child could ask it, yet so deep it has haunted scientists for decades. It's known as the Fermi Paradox, and it begins with a casual lunchtime query. The story goes that in 1950, physicist Enrico Fermi was chatting with colleagues about flying saucers and the potential for interstellar travel when he suddenly blurted out, "But where is everybody?" His point was devastatingly straightforward. The universe is enormous and incredibly old. Our galaxy alone contains hundreds of billions of stars, many of which are billions of years older than our Sun. If even a tiny fraction of these stars have planets capable of nurturing life, and if even a tiny fraction of those life-bearing planets give rise to intelligent, technological species, then the galaxy should be absolutely teeming with civilizations. The sheer numbers suggest that spacefaring empires should have arisen millions, if not billions, of years ago, potentially colonizing the entire Milky Way. So why do we see no signs of them? Why, when we gaze out at the stars, do we find only silence and emptiness? This paradox was later formalized by astronomer Frank Drake with his famous Drake equation. It's not so much a formula to be solved as a framework for thinking about the problem. It multiplies together a series of probabilities: the rate of star formation, the fraction of stars with planets, the number of planets in each system that could potentially support life, the fraction of those where life actually emerges, the fraction where that life becomes intelligent, the fraction that develop technology capable of broadcasting their existence, and finally, the length of time such civilizations might last. Plug in optimistic numbers, that life is common and civilizations are long-lived, and the equation suggests there could be millions of intelligent species in our galaxy right now. Yet, when we multiply all those probabilities, the result we observe with our telescopes is zero. We have found no artifacts, no signals, no visitors. The answer to the equation seems to be one: just us. So what explains this great silence? Scientists have proposed a dizzying array of possible solutions, each more thought-provoking than the last. Perhaps the answer is biological. Maybe the emergence of life itself is an incredibly rare fluke, a statistical miracle that has only happened once. Or perhaps life is common, but the jump from simple single-celled organisms to complex, multicellular animals is the real bottleneck, an evolutionary leap that required such a precise and unlikely series of events that it effectively never occurs. Another grim possibility is that intelligent life is not rare, but it is not long-lived. This is the concept of the Great Filter, a hypothetical barrier that prevents life from progressing to the point of interstellar colonization. The filter could be behind us. We were incredibly lucky to have made it this far, or it could be ahead of us. Perhaps every advanced civilization eventually discovers a technology, like nuclear war or engineered pandemics, that inevitably leads to its own self-destruction. The eerie silence of the cosmos could be a warning, a graveyard of species that failed to overcome their own destructive impulses. Other ideas are less ominous but no less strange. Maybe advanced civilizations are out there, but they have no interest in Star Trek-style galactic empires. They could be exploring inner space instead of outer space, having uploaded their consciousness into vast virtual realities that are far more compelling than the physical universe. Or perhaps they are being deliberately quiet, observing a strict galactic prime directive to avoid interfering with pre-contact species like us. Another fascinating and slightly terrifying idea is the zoo hypothesis, which suggests we are essentially living in a cosmic wildlife preserve, set aside for study by far older beings who are watching us from a distance. Then there is the possibility that we are simply looking in the wrong way. Our searches for extraterrestrial intelligence, like the SETI Institute's efforts to scan the skies for radio signals, are like trying to find a specific fish in all the world's oceans by dipping a teacup over the side of a boat. We've only searched a minuscule fraction of the possible frequencies and directions, and for a vanishingly small amount of time. An advanced civilization might not use radio waves at all, instead communicating with neutrino beams or something else we haven't even thought to look for. The Fermi Paradox ultimately holds up a mirror to humanity, forcing us to confront our own future. Are we the first, the only, or the next to fall? The silence is either a testament to our incredible rarity and good fortune, or it is a sobering preview of our own destiny. It challenges our deepest assumptions about life and our place in the cosmos, reminding us that the universe owes us no answers, and that the greatest discovery we could ever make might be the realization that we are truly, utterly alone. Amidst the profound and unsettling silence of the Fermi Paradox, a single, tantalizing blip on the radar offers a flicker of possibility. It was a warm August evening in 1977, and at Ohio State University's Big Ear radio telescope, a routine survey of the sky was underway, part of the long-running search for extraterrestrial intelligence, or SETI. The system was automated, printing out reams of data on long sheets of paper with columns of alphanumeric codes representing signal strength. For the most part, the printout was a monotonous sea of noise, background static, and the occasional blip of terrestrial interference. But on the night of August 15th, something extraordinary happened. The telescope, fixed in place as the Earth rotated, swept its beam across a patch of sky in the constellation Sagittarius. For exactly 72 seconds, a powerful, focused signal flooded the receiver. It was so intense that it maxed out the equipment's measurement scale. And then, just as suddenly as it appeared, it was gone, never to be heard again. The signal itself was a textbook example of what SETI scientists had been hoping to find. It was a narrowband signal concentrated on one specific frequency, which is a key hallmark of an artificial transmission. Natural cosmic objects like stars or nebulae emit radiation across a broad spectrum of frequencies. A narrowband signal is like a perfectly tuned whistle cutting through the roar of a crowd. It suggests a deliberately engineered source. This one was centered on the hydrogen line at 1420 MHz, a frequency that many scientists consider a logical, universal channel for communication because hydrogen is the most common element in the universe. The signal's intensity rose and then fell in a perfect, smooth curve, exactly as you would expect as the telescope's beam passed by a fixed point in the sky. It was, in every technical sense, the perfect candidate for an interstellar hello. A few days later, astronomer Jerry Amon was reviewing the computer printout. As his eyes scanned the columns of alphanumeric data, he saw the sequence 6EQUJ5. The alphanumeric code was a measure of the signal's intensity, and the values were so far off the chart that he circled them in red pen and in the margin simply wrote, "Wow." That single word of stunned amazement gave the signal its immortal name. In the decades since, the WOW signal has become the single most famous and debated event in the history of SETI. It represents the ultimate what-if moment, and the first order of business for any scientist is to rule out all possible terrestrial or natural explanations. Could it have been a secret military transmission, a bounced signal from a passing satellite, perhaps an outburst from a passing comet? Teams have investigated every conceivable possibility. The frequency of 1420 MHz is actually protected by international agreement, reserved exclusively for astronomical research to prevent earthly interference, making a clandestine human source unlikely. The most recent and detailed investigation focused on the possibility of hydrogen clouds surrounding comets that were in the area at the time. But the comets' positions didn't align perfectly with the direction of the signal, and their hydrogen clouds wouldn't produce such a powerful, narrowband burst. Every proposed natural explanation has, upon close scrutiny, fallen short. No known natural celestial object can produce a signal that matches all of the WOW signal's unique characteristics. It remains to this day a complete anomaly. This leaves us with that breathtaking, spine-tingling possibility. If it was artificial, it came from a star system somewhere in the direction of the constellation Sagittarius, hundreds of light-years away. The 72-second duration is perfectly explained by the fixed telescope listening to a stationary point in the sky as the Earth rotates. We heard it for exactly as long as it took for that point to pass through the telescope's beam. And then we never heard it again. This is the core of the mystery and the source of its enduring fascination. Was it a one-time beacon, a lighthouse pulse sent out by a civilization that has long since vanished, a message that traveled for centuries through the void only to brush past our planet for a single, silent minute? Or was it a continuous signal that we simply haven't managed to find again, like tuning into a radio station for a moment and then losing the frequency forever? The frustration is palpable. We have no way to know and no way to reply. A response sent today would take centuries to arrive. The wow signal is more than just a data point. It is a powerful symbol. It embodies the twin emotions that define the search for extraterrestrial intelligence, a boundless hope and agonizing frustration. It is the hope that we are not alone, that the cosmic silence is not empty but simply waiting for the right moment to be broken. And it is the frustration of a clue that is both perfect and utterly useless, a message without content, a sender without an address. It is a reminder that the universe is vast and ancient, and that our window for listening is still so very small. We have been seriously searching the skies for signs of other civilizations for less than a century, a mere blink of an eye in cosmic terms. The wow signal stands as a ghost in the machine, a single, perfect note in an otherwise silent symphony, challenging us to keep listening, to keep wondering, and to never stop being amazed by the possibility that somewhere out there, another mind might be waiting to be found. Just when we think we've catalogued the universe's greatest spectacles, it reveals something entirely new and bewildering. In 2007, a team of astronomers led by Duncan Lorimer was sifting through old archival data from the Parkes radio telescope in Australia, searching for new pulsars. Instead, they found something that made no sense at all: a single, blisteringly intense burst of radio waves that lasted a mere 5 milliseconds. It was a flash of energy so powerful that it saturated the telescope's detectors, a spike in the data that seemed to come from nowhere and everywhere at once. For years, it was considered a potential glitch, an anomaly so strange that many dismissed it. But then, more were found. We now know this was the first recorded fast radio burst, or FRB, a cosmic event that packs more energy than the sun emits in 80 years into a flash shorter than the blink of an eye. A burst of raw power that arrives from billions of light years away with no obvious source. The defining characteristic of an FRB is its breathtaking brevity and power. These are not sustained signals. They are cosmic gunshots, momentary flashes that appear randomly in the sky and vanish before we can even turn our largest telescopes toward them for a closer look. For a long time, the biggest mystery was whether they were even real celestial objects or just some form of terrestrial interference. Perhaps a microwave oven being opened prematurely at an observatory cafeteria. The tide turned decisively when the Arecibo telescope in Puerto Rico detected an FRB that did something extraordinary. It repeated. This wasn't a one-off event. The same source in a distant galaxy flashed again and again, sometimes in a frantic, storm-like sequence of bursts, other times with long periods of silence in between. This single discovery shattered the idea that all FRBs were caused by cataclysmic, one-time events. It proved they were a genuine astrophysical phenomenon and opened the door to a universe of possibilities, from the violently destructive to the ingeniously constructed. So what cosmic engine could possibly generate such staggering amounts of energy in such an infinitesimally short time? The list of suspects reads like a tour of the universe's most extreme environments. The leading natural candidate is a type of neutron star known as a magnetar. Imagine the core of a massive star collapsed into a sphere the size of a city, but with a magnetic field, SO Chinese letter, it could erase a credit card from halfway across the moon. These objects are cosmic monsters, and theorists propose that starquakes on their surfaces, immense crustal shifts, or sudden magnetic field reconnections could unleash titanic explosions of radio waves, firing out into the cosmos like a lighthouse beam of pure energy. The repeating nature of some FRBs fits well with this idea. A magnetar doesn't necessarily destroy itself in a single outburst, but can have multiple violent episodes throughout its life. But not all FRBs are repeaters, and this is where the mystery deepens. The one-off bursts suggest a truly catastrophic origin, a source that is annihilated in the process of creating the flash. This points toward events like the collision of two ultra-dense neutron stars or the final death throes of a star being consumed by a black hole. Events so violent they are among the most energetic in the universe since the Big Bang. There are even more exotic ideas on the table, like cosmic strings theoretical, one-dimensional defects in the fabric of space-time left over from the universe's birth. The snapping of such a string could, in theory, release an unbelievable amount of energy in a radio burst. Then, of course, there is the most speculative, yet most captivating possibility. Could some FRBs be the product of technology? The idea is not as far-fetched as it might seem. The bursts are intense, focused, and span a wide range of frequencies, characteristics that could be consistent with an engineered signal. Some scientists have playfully proposed they could be evidence of interstellar light sails, massive structures powered by beams of radio waves to push spacecraft near the speed of light. A misaligned beam from such a system sweeping across our galaxy could appear to us as a fleeting, incredibly powerful flash. Or perhaps they are beacons, a means of communication or navigation on a galactic scale that is simply too advanced for us to yet comprehend. While this remains a highly speculative minority view, it underscores just how extraordinary these signals truly are. They push us to consider all possibilities, no matter how unconventional. The key to solving this puzzle lies in the new era of discovery ushered in by telescopes like CHIME, the Canadian Hydrogen Intensity Mapping Experiment. Unlike traditional radio dishes that look at a tiny patch of sky, CHIME is a stationary array that acts like a wide-angle camera, scanning the entire northern sky every single day. This has revolutionized the field. CHIME is now detecting FRBs by the dozens, sometimes multiple events in a single day, providing a vast new treasure trove of data. This flood of discoveries is allowing astronomers to see patterns for the first time. We now know that FRBs come from galaxies far beyond our own, from both young, star-forming galaxies and old, quiet ones. Some even show strange, periodic patterns in their activity, flaring up on a predictable cycle that could be a clue to their origin, perhaps linked to the orbital motion of a binary star system. Yet with every new detection, the mystery seems to grow more complex rather than less. The simple question of what causes an FRB now has a myriad of potential answers, and it's likely that FRBs are not one but many different types of phenomena. Some are repeaters, some are one-offs, some are highly polarized, suggesting they traveled through incredibly strong magnetic fields, while others are clean. This diversity is a classic signature of a new field of astronomy. We are still in the phase of collecting and categorizing, trying to piece together a classification system for something we don't yet fully understand. Each burst is a message from a distant galaxy, a brief, encrypted telegram that contains clues about the conditions that created it and the vast stretches of intergalactic space it has traveled through. The puzzle of fast radio bursts is a powerful reminder that the cosmos is still full of surprises, that even in the silent dark between the stars, there are flashes of brilliance waiting to be seen, each one a challenge to our understanding and an invitation to dream bigger. In the vast, silent expanse of interplanetary space, even the smallest unexpected motion can become a monumental mystery. As our robotic envoys, the Pioneer 10 and 11 probes, journeyed beyond the orbit of Pluto and into the outer darkness, scientists tracking their precise trajectories noticed something deeply puzzling. Both spacecraft were experiencing a tiny but constant and unexplained deceleration back toward the sun. It was an effect so minuscule it would be like a single sheet of paper gently resting on your palm. Yet over the immense distances these probes were traveling, this persistent tug was undeniable and for a time utterly baffling. Here was a force acting upon humanity's farthest flung objects that our understanding of gravity could not account for, a ghostly hand reaching out from the void to ever so slightly apply the brakes. For years, this pioneer anomaly captivated physicists and sparked countless theories. The most tantalizing explanations pointed toward revolutionary new physics. Could it be the first local signature of dark matter, a halo of unseen particles gravitationally clinging to our solar system and subtly altering the paths of spacecraft? Or was it something even more profound, a sign that our theory of gravity itself, Einstein's magnificent general relativity, needed a slight modification at the very largest scales, a tweak that would only become apparent in the weak gravitational fields of the deep solar system? The anomaly became a classic scientific whodunit, with the potential culprit being everything from exotic new forces to previously undetected dimensions of space. Yet, as is often the case in science, the most thrilling answer is not always the correct one. After decades of painstaking analysis, which involved recovering old telemetry data and building incredibly detailed computer models of the Pioneer spacecraft, a team of researchers pinpointed a far more mundane cause. The probes were powered by radioactive plutonium pellets, whose decay generated heat and therefore electricity. This process meant the spacecraft were essentially lopsided little power plants, radiating heat preferentially from one side. The team realized that this emitted thermal radiation, these tiny infrared photons pushing off the craft's surface, acted like a minuscule but continuous rocket thrust directed back toward the sun, perfectly accounting for the vast majority of the observed anomalous deceleration. It was a brilliant piece of scientific detective work, solving a mystery with careful, meticulous engineering analysis. But the story doesn't end with a simple, closed case. While thermal radiation explains most of the effect, some researchers argue that tiny discrepancies might still remain in the data, a residual anomaly that the heat model doesn't entirely erase. This intrigue is compounded by another curious fact. The Voyager spacecraft, which followed similar paths out of the solar system, did not show the same pronounced effect. This difference is likely because the Voyager probes, with their three-axis stabilization and different design, were far less susceptible to the lopsided thermal push that affected the spin-stabilized Pioneers. Their trajectories were governed more by thruster firings for course correction, which would have masked any tiny, constant force. As one NASA, a scientist involved in the investigation, reflected, "It's a reminder that even our best models have gaps, and nature always has a way of surprising us with the details." So, does this mean the book is completely closed on the Pioneer anomaly? Not necessarily. That lingering whisper of a discrepancy and the sheer allure of the original mystery continues to inspire questions. Could there be a small component of the deceleration that truly is new physics, perhaps a subtle effect of the local distribution of dark matter that the thermal model just doesn't capture? The puzzle serves as a powerful lesson in humility. It shows that even within our own celestial neighborhood, a region we are now beginning to explore with new missions, the fundamental forces we think we understand might still hold subtle surprises. The Pioneers, now silent and drifting toward the stars, performed one final experiment for humanity, teaching us that the universe reveals its secrets not only in the grand sweep of galaxies, but also in the almost imperceptible drift of a lonely spacecraft. Beyond the orbit of Neptune, the solar system does not simply fade into an empty, starry void. Instead, it gives way to a vast, donut-shaped region of frozen remnants known as the Kuiper Belt, a distant realm of icy worlds and dwarf planets like Pluto that represents the preserved building blocks of our planetary system. For decades, our models of how the solar system formed predicted that this population of objects should continue, with their numbers gradually thinning out for a significant distance. Imagine a gently sloping beach where the sand gets finer and sparser the further you walk into the water. But that's not what we see. When astronomers began to meticulously map the orbits of these distant Kuiper belt objects, or KBO, they discovered something deeply puzzling. At a distance of about 50 astronomical units from the Sun, that's 50 times the distance from Earth to the Sun, the number of detectable objects doesn't just thin out, it plummets. It's a veritable cliff edge in space, a sudden and dramatic drop-off in the population of these frozen bodies, as if some great celestial broom had swept the outer solar system nearly clean, or the construction materials for planets simply ran out. This so-called Kuiper Cliff presents a direct and significant challenge to our standard narrative of solar system formation. The leading model, known as the NICE model, suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune migrated outward from their original birthplaces early in the solar system's history. As they moved, their immense gravity would have scattered countless icy planetesimals outward, populating the Kuiper belt and the even more distant Oort cloud with a smooth, continuous distribution of objects that slowly decreases in density with distance. The existence of a sharp cliff, a distinct and unexpected boundary, means this story is either incomplete or incorrect. It's as if an archaeologist, carefully excavating an ancient city, suddenly found that all artifacts simply stopped at a specific line, suggesting a forgotten catastrophe or a hidden barrier that shaped the entire site. So what could have created this stark boundary in our own cosmic backyard? Astronomers have proposed several compelling and quite dramatic theories. The most tantalizing idea is that our solar system is not yet fully mapped, that a large, undiscovered planet, often referred to as Planet 9 or Planet X, lurks in the extreme outer darkness. This hypothetical world, estimated to be several times the mass of Earth on a highly elongated orbit that takes it hundreds of astronomical units from the Sun, could be the gravitational architect of the Kuiper Cliff. As it travels its immense, lonely path, its gravity would violently perturb the orbits of any smaller objects that venture too close, either flinging them inward toward the Sun, ejecting them from the solar system entirely, or shepherding them into orbits that are tilted and clustered in ways we are only beginning to recognize. Over billions of years, this process could have efficiently cleared out a vast swath of the outer Kuiper belt, creating the sharp boundary we observe today, and leaving behind only those objects in stable, resonant orbits that avoid close encounters with the perturbing giant. But a hidden planet is not the only possible sculptor. Another fascinating theory reaches back to the very birth of our Sun, suggesting we were not always an only child. Most stars are born in dense clusters alongside thousands of stellar siblings. It is entirely possible that our Sun had a twin, a binary companion that formed with it from the same cloud of gas and dust. If this sibling star passed close enough to our infant solar system before the cluster dispersed, its gravity could have acted like a thief, stripping away a huge portion of the outer planetesimal disk and carrying it off into interstellar space. This stolen material would have left our system with a sharply truncated Kuiper belt, a permanent scar from a close encounter in its infancy. This stolen twin theory is difficult to prove, as that sibling star would have long since drifted away into the galactic void, but it remains an elegant and plausible solution to the puzzle. The quest to solve this mystery is driving a new generation of sky surveys. Instruments like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, or LSST, are designed to methodically scan the entire visible sky with unprecedented depth and frequency. This powerful observatory will be our best tool yet for finding extremely faint, slow-moving objects in the farthest reaches of our solar system. If Planet 9 is out there, LSST has a very strong chance of finally revealing its presence, confirming one of the most exciting potential discoveries in modern astronomy. But even if no new planet is found, the survey will provide an incredibly detailed census of the Kuiper Belt's population, allowing us to map the precise shape and extent of the cliff edge with more accuracy than ever before. This data could point toward other explanations, perhaps involving the complex dynamical interactions between the giant planets themselves during the solar system's violent youth. The Kuiper Cliff is more than just a curiosity. It is a profound clue etched into the frozen debris of our solar system, a silent witness to events that occurred billions of years ago, waiting for us to decipher its story and finally understand the true extent and history of our celestial home. While most stars shine with a reassuring clockwork regularity, one star in the constellation Cygnus behaves like nothing else we have ever seen. Officially catalogued as KIC 8462852, it's far better known by the nickname it earned from the astronomer who brought its strangeness to the world, Tabby's star. Named for Tabetha Boyajian, this seemingly ordinary star, slightly larger and hotter than our own Sun, has become the single most enigmatic object in our galaxy because of one baffling behavior: it dims. Not in the gentle, rhythmic way caused by an orbiting planet, which typically blocks less than 1% of a star's light, but in dramatic, irregular, and catastrophic plunges in brightness. In 2015, data from the Kepler Space Telescope revealed that this star's light had dropped by a staggering 22% on one occasion, and by 15% on another, with no discernible pattern. It was as if something colossal and utterly opaque was passing in front of it, something on a scale that defies any conventional astronomical explanation. The immediate challenge for scientists was to find a natural cause for this bizarre light curve, and the list of suspects is long and creative. The first and most popular idea involved a massive, chaotic swarm of comets. Perhaps a family of icy bodies numbering in the hundreds of thousands had been disturbed from their distant orbits and were now spiraling inward, surrounded by immense clouds of dust and debris that could collectively block a huge portion of the star's light. Other theories pointed to dust from a colossal planetary collision, a recent and violent event that left the star shrouded in the remains of a shattered world. Some even proposed that the star itself was going through a unique and late-stage phase of planetary formation, where a thick, clumpy disk of material was still coalescing into planets, casting deep, irregular shadows. Each of these natural explanations was plausible in its own way, but upon closer inspection, each began to fray at the edges. Detailed follow-up observations, particularly in the infrared spectrum, failed to detect the excess heat that such vast amounts of dust and debris should be emitting. If a huge cloud of cometary dust or planetary rubble was causing the dimming, it should be glowing with warmth, but Tabby's star remained curiously cold, offering no such thermal signature. It was this stubborn refusal to conform to any known natural model that opened the door to a far more speculative, yet utterly captivating possibility. Could we be witnessing something artificial? The idea was first seriously floated in a study that suggested the dimming pattern was consistent with a vast, incomplete megastructure orbiting the star, something like a Dyson swarm. Proposed by physicist Freeman Dyson in the 1960s, such a structure would be the ultimate project for a civilization far more advanced than our own, a network of colossal energy collecting satellites or habitats encircling their star to harness its entire energy output. The irregular, deep-dimming events could be explained by the transit of these massive construction projects, each one blocking a significant portion of the star's light as it passed in front of our telescopes. As Tabetha Boyajian herself noted with a sense of awe, the strange signal was indeed something you would expect an alien civilization to build. This wasn't a claim of discovery, but a sober acknowledgement that the most extreme explanation had to at least be on the table, given the data's refusal to cooperate with more conventional theories. The scientific response to this thrilling hypothesis was not to dismiss it, but to subject it to the most intense scrutiny imaginable. Astronomers have since trained a vast array of instruments on Tabby's star, from the Hubble Space Telescope to massive radio antennae listening for artificial signals. While the star has continued to dim, sometimes in slow, multi-year declines and other times in sudden, sharp dips, no clear evidence of technology has emerged. No telltale radio transmissions or laser pulses have been detected, and further analysis has shown that the dimming affects different colors of light slightly differently, a characteristic that often points toward dust-sized particles rather than solid, opaque megastructures. The current consensus leans toward some kind of exotic, and still poorly understood, astrophysical dust as the primary culprit, perhaps made of a material that doesn't behave like the dust in our own solar system. Yet, a definitive consensus remains elusive. The case of Tabby's star is far from closed. Its enduring mystery doesn't stem from a single, simple answer, but from its ability to consistently defy every answer we try to impose upon it. It captivates us not because we are sure aliens are building there, but because it sits perfectly at the boundary between the known and the unknown. It represents a class of object we never knew could exist, a phenomenon that pushes our understanding of stellar behavior and planetary systems to their absolute limits. It forces us to ask, in the most concrete terms possible, how we would even recognize the signature of a technology so vast it could rearrange a star system. Is the absence of evidence for aliens evidence of their absence? Or are we simply not yet clever enough to see it? Tabby's star is a perpetual question mark hanging in the sky, a constant reminder that the universe is capable of wonders we have not yet dreamed of, and that the most exciting phrase in science will always be, "That's funny." In October 2017, astronomers working with Pan-STARRS telescope in Hawaii spotted a tiny, fast-moving point of light that immediately stood out from everything else in the sky. It was not orbiting the sun, it was just passing through, and it was moving so fast that it would eventually leave our solar system forever. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, and it instantly made history as the very first object ever detected from interstellar space. This was not a native of our solar system. It was a true visitor from the vast ocean between the stars, and it carried with it secrets that would ignite one of the most passionate debates in modern astronomy. Initial observations revealed a string of bizarre properties that made Oumuamua utterly unique. First, its path around the sun couldn't be explained by gravity alone. Like a car unexpectedly surging forward after coasting downhill, Oumuamua exhibited a tiny but definite non-gravitational acceleration. It was being pushed by something, and in the solar system, that something is almost always outgassing. When a comet's icy surface is heated by the sun, it vents gas and dust into space, which acts like a natural thruster, subtly altering its orbit. But here was the second, and most critical, anomaly. Oumuamua showed no visible signs of this activity. It had no coma, the fuzzy envelope of gas and dust that surrounds a comet's nucleus, and no tail, the classic features we've seen on every other comet humanity has ever observed. It was completely inert, a dark, silent traveler. Then there was its shape. By measuring how its brightness changed dramatically as it tumbled through space, astronomers inferred that Oumuamua was highly elongated. Its dimensions were estimated to be roughly 10 times as long as it was wide, a shape unlike any known asteroid or comet in our solar system, which tend to be more lumpy or spherical. Imagine a cosmic cigar or, as some have suggested, a flat pancake, tumbling end over end through the void. This bizarre form only deepened the mystery of its composition and origin. What natural process could create such an object? Was it shorn off a planet by a colossal impact? Was it a fragment from a shredded comet? Every conventional explanation seemed to struggle with one of its strange traits. The most contentious and thrilling hypothesis came from Harvard astronomer Avi Loeb, who argued that we should seriously consider an artificial origin. He pointed out that the non-gravitational acceleration was smooth and steady, unlike the typically jerky, unpredictable outgassing of a comet. More provocatively, he calculated that the acceleration could be perfectly explained if Oumuamua were an extremely thin, lightweight object pushed by the radiation pressure from sunlight, a light sail. Humanity is already experimenting with this technology. Projects like Breakthrough Starshot aim to send tiny, sail-equipped probes to nearby stars. Could Oumuamua be a discarded piece of an ancient extraterrestrial light sail, a derelict from a civilization that chose to explore the galaxy not with massive ships but with tiny, resilient probes? As Loeb himself has consistently urged, we should be open-minded and search for evidence rather than assume it's natural. His argument wasn't that it definitely was aliens, but that the possibility should be on the table, especially when natural explanations were proving so unsatisfactory. The scientific pushback was swift and robust. Many astronomers argued that while Oumuamua was strange, invoking aliens was a last resort, not a first option. They proposed alternative natural explanations. Perhaps it was a chunk of solid hydrogen ice, venting hydrogen gas so pure it would be invisible to our telescopes. Or maybe it was a nitrogen iceberg sheared from the surface of a Pluto-like exoplanet, with nitrogen sublimation providing the unseen thrust. These ideas are also highly speculative, but they remain within the realm of known, if exotic, astrophysics. The fundamental problem is that Oumuamua was discovered as it was already leaving our solar system. We had only a few precious weeks to observe it before it became too faint to study, and we never got a clear picture of it. We are left with a handful of tantalizing data points and a universe of possibilities. Ultimately, the greatest legacy of Oumuamua may not be a definitive answer, but the profound question it forces us to confront. Are we alone? And if we are not, what might the artifacts of other civilizations look like? This lonely, silent scout challenged our assumptions about how solar systems form and what kinds of objects travel between them. It underscored that our inventory of cosmic visitors is based on a sample size of one, and that one is deeply weird. It taught us that interstellar space is not empty. It is likely filled with a constant rain of such objects, and we have only just developed the technology to notice them. The next time an interstellar visitor is detected, we will be ready with telescopes primed and missions perhaps even designed to intercept it. Until then, Oumuamua remains a perfect cosmic Rorschach test, a dark, tumbling enigma that reveals just as much about our own hopes, fears, and boundless curiosity as it does about the secrets of the galaxy. For nearly a century, one number has stood as the single most important parameter in all of cosmology, the golden key to unlocking the universe's past, present, and future. It is the Hubble constant, a deceptively simple value that measures the current rate of the universe's expansion. Determining this number with precision has been the holy grail of astronomy, because everything, the age of the universe, the nature of dark energy, the ultimate fate of all we see, depends on it. And now, in what should be a triumphant era of unparalleled observational power, this foundational pillar of modern science is showing a hairline crack that threatens to bring the entire edifice down. The most precise measurements ever made, using two completely different and seemingly ironclad methods, are yielding two different, stubbornly incompatible answers. This isn't a minor quibble over decimal points. It is a direct, unignorable clash that cosmologists have ominously dubbed the Hubble Tension. To understand the gravity of this conflict, we need to look at the two ways we measure this crucial number. The first method is like a cosmic genealogy, tracing the universe's history back to its infancy. We use exquisitely detailed maps of the cosmic microwave background, the afterglow of the Big Bang captured by satellites like Planck. This ancient light reveals the precise conditions of the early universe, and by plugging these measurements into our standard model of cosmology, the lambda-CDM model, which includes dark matter and a cosmological constant for dark energy, we can run the clock forward 13.8 billion years and predict what the expansion rate should be today. This is a top-down, model-dependent approach, and it gives us a very specific value for the Hubble constant, around 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, a staggering 3.26 million light-years, a galaxy is moving away from us at 67 kilometers per second faster. The second method is more like a straightforward cosmic cartography project, building a distance ladder out into the nearby universe. Astronomers use pulsating stars called Cepheid variables as their primary rung on this ladder. These stars have a wonderful property. Their pulsation period is directly tied to their true, intrinsic brightness. By measuring how fast they pulse, we know how bright they should be, and by comparing that to how dim they appear to us, we can calculate their exact distance with remarkable accuracy. We then look for these Cepheids in galaxies that also contain another, even brighter kind of stellar explosion, Type 1a supernova. These supernovae are so brilliantly uniform they are known as standard candles, and by calibrating their peak brightness using the Cepheids, we can use them to measure distances to galaxies far, far across the universe. By measuring both the distance and the redshift, the speed at which these galaxies are receding from us, we can directly calculate the Hubble constant right now. This bottom-up empirical method, championed by teams like the one led by Nobel laureate Adam Rees, gives a starkly different answer, approximately 73 kilometers per second per megaparsec. A difference of about 6 might not sound like much, but in the world of precision cosmology, it is a yawning chasm. The error bars on each measurement have been squeezed down to a mere 1 or 2%, and yet the two values refuse to meet. They are separated by a gap of about 5 sigma, a term in statistics that means there is less than a 1 in a million chance that this discrepancy is a mere fluke. As renowned cosmologist Wendy Friedman has stated, this could be a clue that something is missing in our standard model. And that is the terrifying and thrilling implication. This isn't just a debate about a number. It is a potential sign that our understanding of the fundamental constituents and laws of the universe is incomplete. Theories for what might be causing this tension are as fascinating as they are varied. Perhaps dark energy is not a constant after all, but a dynamic force that has been changing in strength over the history of the cosmos, subtly altering the expansion rate in a way our standard model doesn't account for. Maybe dark matter possesses unknown properties, allowing it to interact with itself or with light in ways we haven't anticipated. There are even more exotic ideas, such as the existence of a new type of relic particle from the Big Bang, or that the early universe underwent a brief, secondary phase of accelerated expansion that left a hidden imprint on the Hubble constant. The most unsettling possibility of all is that our cherished cosmological principle, the idea that the universe is uniform and isotropic on large scales, is wrong, and that we live in a giant cosmic void, a vast underdense region of space that is locally expanding faster than the average, skewing our nearby measurements. Resolving this crisis is now a primary mission for the world's most powerful observatories. The James Webb Space Telescope, with its infrared vision, is peering through the dust that obscures Cepheid variables, aiming to refine the cosmic distance ladder with unprecedented clarity. Meanwhile, new projects are looking for entirely independent ways to measure the expansion, such as using the gravitational waves from colliding neutron stars as standard sirens. Each new observation is a critical test. Will the tension dissolve, revealing a subtle systematic error in our measurements that we can finally correct? Or will it hold firm, forcing us to accept that we are on the cusp of a revolution in physics, a paradigm shift that will rewrite our cosmic story and reveal a universe far stranger and more wonderful than we ever imagined? The Hubble constant is more than a number. It is the universe's pulse, and right now, it's telling us two different stories at once. After exploring the unsettling possibility that our cosmic neighborhood might be shaped by unseen giants like the Great Attractor, we now turn to a discovery that strikes at the very heart of cosmology's most cherished principle. The universe, we have long believed, should be a grand, democratic expanse. On the largest scales, it should have no center, no edge, and no preferred direction, a concept known as the cosmological principle. It's the idea that the cosmos is isotropic and homogeneous, meaning it looks roughly the same in every direction and from every location. This isn't just philosophical. It's the foundational assumption that allows us to extrapolate the laws of physics from our tiny corner of the universe to the cosmos as a whole. But what if this bedrock principle is wrong? What if the universe, in some subtle but significant way, has a built-in preferred direction, a cosmic north that challenges our entire understanding of reality? This is the profound and unsettling mystery known as the axis of evil. The evidence for this cosmic heresy comes from our most trusted map of the primordial universe, the cosmic microwave background. This ancient light is the crown jewel of cosmology, a snapshot of the infant cosmos that has beautifully confirmed so many of our predictions about the Big Bang. Its overall uniformity is a stunning validation of the cosmological principle. But when scientists began to analyze the tiny, 1 part in 100,000 fluctuations in this background radiation, the seeds of all future galaxies, they found something they never expected. These fluctuations are not completely random. On the very largest scales, they appear to be aligned or correlated with the plane of our own solar system and the direction of the sun's motion through space. It's as if the universe's earliest structures were somehow aware of our local celestial geography billions of years before our solar system even existed. This bizarre and unexpected correlation was so unnerving that researchers, with a touch of dark humor, dubbed it the axis of evil, a name that has stuck precisely because it captures the threat this anomaly poses to our standard models. The immediate and most comfortable explanation is that we are simply seeing a statistical fluke. The universe is vast, and even in a perfectly random and isotropic cosmos, there's always a chance that some patterns will emerge that look strangely significant to us. We might just be the unlucky observers who happen to see a grand cosmic illusion, a trick of the light on the largest possible scale. This is the null hypothesis, and many cosmologists cling to it, hoping that more precise data from future observatories will eventually smooth out this apparent alignment and restore order to the universe. But the problem is that the anomaly has refused to go away. The Planck satellite, which provided the most detailed and precise map of the cosmic microwave background ever created, didn't resolve the axis of evil, it confirmed it. The data from Planck is exquisitely clean, and the team behind the mission ran exhaustive tests to rule out instrument error, foreground contamination from our own galaxy, or any other systematic glitch. The alignment persists. This forces us to consider the far more thrilling possibility that it is real and that its implications are revolutionary. If the universe does have a preferred axis, a fundamental directionality woven into the fabric of space-time itself, then our cosmological principle is broken. We are not living in a featureless, democratic cosmos, but in a universe with architecture with a grain to it like cosmic wood. What could possibly cause such a fundamental directionality? The theories are as mind-bending as the puzzle itself. Perhaps this axis is a fossil imprint from a time before the Big Bang, a remnant of some exotic physics that set the initial conditions for inflation. It could be a scar from a collision with another universe in the vast multiverse, a permanent warp in our local space-time from a long-ago encounter with a reality beyond our own. Some have even proposed that dark energy or dark matter might not be uniform, but could have a directional component, flowing like a cosmic wind and imparting a subtle preference to the expansion and structure of the universe. Each of these ideas pushes the boundaries of physics, suggesting that our current models are merely a rough sketch of a far more complex and intricate reality. This leads us to the most profound and humbling question of all. Does this potential axis somehow make our location special? For centuries, science has been moving us away from a cosmic center stage, from the geocentric model to the principle of mediocrity, which insists there is nothing special about our place in the universe. The axis of evil whispers a dangerous counter-narrative. Could it be that, against all odds, we are in a privileged position to observe this alignment? Or does this axis exist everywhere, meaning that any observer, anywhere in the cosmos, would look out and see the large-scale structure of the universe aligned with their own local motion? The very fact that we have to ask these questions is a monumental shift. It forces us to confront the possibility that our place in the cosmos might not be entirely random, that the universe may have an architecture that is both vast and strangely ordered, a design we are only just beginning to perceive. In the fiery crucible of the universe's first moments, a process of cosmic alchemy was underway that would forge the very first atoms. This era, known as Big Bang nucleosynthesis, occurred within the first 3 minutes after the birth of everything, a fleeting period where the entire cosmos was hot and dense enough to act as a nuclear fusion reactor. The models describing this process are breathtakingly precise, predicting with remarkable accuracy how much of the lightest elements should have been cooked into existence. For hydrogen and helium, the predictions are a stunning success. The amount of helium-4 we observe in the oldest stars and cosmic clouds matches the theoretical prediction almost exactly, a powerful confirmation that we understand the broad strokes of the universe's earliest chapters. But for one element, the numbers tell a very different story. The models insist that for every 10 billion atoms of hydrogen, there should be about 5 atoms of lithium-7. Yet when we look out at the oldest stars in the halo of our galaxy, ancient stellar relics that formed from the pristine gas of the early universe, we find only about 1 or 2 lithium atoms for every 10 billion hydrogen atoms. A significant fraction of the universe's primordial lithium is simply missing, and this discrepancy has stubbornly resisted explanation for decades. this is not a case of imprecise measurements. Astronomers have used the world's most powerful telescopes, like the Very Large Telescope in Chile, to carefully analyze the atmospheres of these ancient suns. The results are consistent and baffling. The lithium abundance is roughly 3 times lower than our best theoretical calculations say it should be. This isn't a minor accounting error, it's a glaring deficit in the cosmic ledger. The puzzle is particularly vexing because the predictions for Big Bang nucleosynthesis are so robust, based on well-understood nuclear physics and the measured density of ordinary matter in the universe. The calculations themselves are not in serious doubt, which means the problem must lie in our understanding of the physics that took place during those first few minutes, or in what happened to the lithium afterward. As one cosmologist aptly put it, it's a small problem that points to big gaps. We are being presented with a clear signal that something is missing from our story of the universe's infancy, a subtle clue etched into the composition of the oldest stars. So where did the lithium go? Scientists have pursued 2 main lines of investigation. The first possibility is that the lithium was created in the correct amount by the Big Bang, but was subsequently destroyed somewhere along the way. Perhaps these ancient stars, over their billions of years of life, have internal processes that slowly destroy lithium, dragging it down from their atmospheres into their hot interiors where it is fused into heavier elements. The problem is that stellar physics models struggle to explain how this could happen uniformly across so many different types of old stars without leaving other, obvious imprints on their chemical makeup. Alternatively, could the lithium have been destroyed before these stars even formed? Maybe the interstellar medium in the early galaxy was more efficient at breaking down lithium atoms than we currently understand. While these astrophysical solutions are plausible, they have so far failed to fully close the gap, leaving many researchers to suspect the answer lies not in stars, but in the physics of the Big Bang itself. This leads to the second and far more thrilling possibility that our models of the primordial universe are incomplete. Could there have been unknown particles or forces at play during those first few minutes that altered the nuclear reactions? One compelling idea involves a hypothetical particle called the action, originally proposed to solve a separate puzzle in particle physics. Actions could have been produced in the early universe, and their subsequent decay might have injected extra photons into the primordial soup. This sudden influx of energy could have shifted the balance of nuclear reactions, reducing the final yield of lithium-7 without significantly affecting the amounts of hydrogen or helium. Other theories propose modifications to the nature of fundamental particles themselves, such as variations in the properties of neutrons or subtle changes in the fundamental constants of nature during that brief, intense period. These are not wild guesses, they are serious attempts to reconcile a clear observational fact with our theoretical framework, and they demonstrate how a tiny anomaly in astrophysics can force us to confront the very foundations of particle physics. The lithium problem, therefore, is a beautiful example of how science progresses. It starts with a small, nagging inconsistency, a number that doesn't quite add up. But instead of dismissing it, scientists relentlessly pursue it because they understand that such tiny cracks in an otherwise solid edifice can sometimes be the first sign of a revolutionary discovery. The missing lithium is a ghost from the dawn of time, a silent witness to processes we have not yet imagined. It asks us to consider that the universe's first moments were even more complex and mysterious than we have dared to believe, and that the answers to some of our biggest questions may be hiding in the subtle chemistry of the oldest stars in the sky. General relativity gives us a breathtakingly powerful description of gravity. painting the cosmos as a dynamic fabric of space-time curved by mass and energy. It allows us to predict the orbits of planets, the bending of starlight, and even the existence of black holes with stunning accuracy. But this magnificent theory, for all its power, contains the seeds of its own downfall. It predicts that when a sufficiently massive star collapses under its own weight, or when matter is compressed beyond a certain point, nothing can stop the inevitable. The collapse continues forever, crushing all matter into an infinitely small point of infinite density, a place where the curvature of spacetime becomes infinite and the very laws of physics, as we know them, simply cease to have meaning. This terrifying point is known as a singularity, and according to our best understanding of gravity, one sits at the heart of every single black hole, a silent monument to the limits of human knowledge. The problem with a singularity isn't just that it's bizarre, it's that it's a glaring signpost that our theory is incomplete. In the real world, physics abhors infinity. An infinitely small point with infinite density is not a physical concept we can work with. It's a mathematical warning that we have pushed Einstein's beautiful equations into a regime where they no longer apply. It's the equivalent of seeing your car's speedometer needle spin right off the dial. It doesn't mean your car is moving at infinite speed. It means the instrument wasn't designed to measure what's actually happening. The singularity is that broken dial, telling us that to understand the core of a black hole, we need a new set of rules, a theory that can marry the cosmic gravity of general relativity with the bizarre, probabilistic world of the very small described by quantum mechanics. We need a theory of quantum gravity. For decades, the world's brightest theoretical physicists have been engaged in this monumental quest, and they have approached the problem from dramatically different angles. One promising path is loop quantum gravity. This theory proposes that spacetime itself isn't smooth and continuous, but is instead woven from tiny, finite loops, a fabric of space that has a finite, granular structure. Think of it like a digital photograph. If you zoom in on a beautiful, smooth image on your screen, you eventually see the individual pixels. Loop quantum gravity suggests spacetime has pixels, a smallest possible unit of volume. In this view, matter cannot be compressed into an infinitely small point because it eventually reaches this smallest possible size. The collapse would stop, and the singularity would be replaced by a highly dense but finite core of matter. Some models even suggest that this could cause a quantum bounce, where the compressed matter rebounds, potentially spewing it out into a new region of spacetime, perhaps even giving birth to a new universe on the other side of what we perceive as a black hole. Another, even more ambitious framework is string theory. It makes the astounding proposition that the fundamental building blocks of the universe are not zero-dimensional points, but tiny, vibrating one-dimensional strings. The different vibrational patterns of these strings manifest as different particles and forces. In this elegant vision, the apparent conflict between gravity and quantum mechanics dissolves because everything at its base is made of the same stuff, strings. When applied to black holes, string theory has produced some remarkable insights, particularly through the concept of holography, which we discussed earlier. It suggests that the information about what falls into a black hole is not lost in a singularity, but is encoded on its surface. Some string theory models propose that the center of a black hole might not be a point of infinite density, but a tangled, fuzzy ball of strings, a fuzzball, that has a complex, though still incredibly dense, structure without any singularities at all. Yet, for all their mathematical beauty and promise, these theories remain just that, theories. They have yet to make a concrete, testable prediction that can be verified by experiment or observation. The energies required to probe the quantum nature of gravity are so unimaginably high that they are far beyond the reach of any particle collider we could ever build. So we are left with a profound and haunting question, perhaps the most fundamental in all of physics. What truly happens at the heart of a black hole? Is it a gateway to another cosmos, a dense but finite knot of quantum spacetime, or simply a dead end where the universe itself winks out of existence? This puzzle is the ultimate challenge because it forces us to confront the limits of our own understanding. It asks us to imagine a reality where space and time as we know them come to an end, and to conceive of a new physics that can take over where the old one fails. The singularity is not just a problem to be solved, it is the final frontier of theoretical exploration, a dark mirror held up to our current knowledge, reflecting back only the questions we have yet to answer. From the crushing densities of black holes to the ghostly whispers of dark matter, we have explored cosmic puzzles that span the vastness of space and time. But now we arrive at a mystery that is, in many ways, the most intimate and profound of all. It doesn't require a telescope to ponder. It is written into the very fabric of our own existence. The puzzle is this: how did inanimate matter, the simple atoms and molecules that make up stars and dust clouds, make the incredible leap to become something we call alive? How did chemistry become biology, and in doing so, give rise to a universe that can, for the first time, look back upon itself and ask how it came to be? The geological record on Earth offers our first tantalizing clue, and it is a deeply suggestive one. Life appears to have emerged on our planet with what seems, in cosmic terms, to be startling speed. The Earth itself formed around 4.54 billion years ago, a molten and violent world bombarded by asteroids in a period known as the Late Heavy Bombardment. Yet, the earliest compelling evidence for life, fossilized microbial mats called stromatolites, dates back to around 3.7 billion years ago. This suggests that within just 700 million years of the planet cooling enough to have liquid water, and perhaps much faster, the basic processes of life had already taken root. This rapid emergence hints that under the right conditions, the transition from non-life to life might not be an astronomically improbable fluke, but a natural, almost inevitable chemical process. If it happened so quickly here, could it be a common narrative written into the laws of the universe? But what was that process? How did simple molecules become complex ones? And how did those complex molecules begin to organize, replicate, and eventually evolve? This is where our certainties end and the grand, fascinating speculation begins. One of the most influential ideas is the RNA world hypothesis. RNA is a miraculous molecule. It can both store genetic information like DNA and catalyze chemical reactions like a protein enzyme. This dual talent suggests that a world based solely on RNA could have been a stepping stone, a simpler precursor to our current DNA-RNA protein system. In this ancient world, a single self-replicating RNA molecule could have acted as both the blueprint and the builder, kickstarting the process of evolution. Scientists have even created such self-replicating RNA in labs, demonstrating that the idea is chemically plausible. Yet, the puzzle remains: how did these complex RNA molecules form spontaneously from the primordial soup? The building blocks of RNA are delicate and difficult to synthesize under probiotic conditions, leaving a significant gap in the story. Other theories look to specific environments on the early Earth that could have provided the perfect crucible for life's genesis. Deep-sea hydrothermal vents, particularly alkaline vents, are a compelling candidate. These are not violent volcanic vents, but porous, rocky structures that seep warm, mineral-rich water into the ancient ocean. They create a natural electrochemical gradient, a gentle, continuous flow of protons not unlike the one that powers every living cell today. This constant, free energy source could have driven the formation of ever more complex organic molecules, safely nestled within the tiny pores of the rock that acted as the first primitive cells. Alternatively, the panspermia hypothesis suggests that we might be looking in the wrong place entirely. This idea proposes that the basic ingredients for life, or even life itself in a microbial form, could have been delivered to Earth by comets, asteroids, or interstellar dust. While this elegantly sidesteps the problem of Earth's rapid timeline by making life a galactic phenomenon, it merely moves the mystery elsewhere. It does not answer the fundamental question of how life began. It just suggests it began somewhere else. Our quest to recreate that moment of genesis in a laboratory began in earnest with the famous Miller-Urey experiment in 1952. By simulating the supposed atmosphere of the early Earth with water, methane, ammonia, and hydrogen, and zapping it with electrical sparks to mimic lightning, Stanley Miller and Harold Urey found that they could produce a rich broth of organic molecules, including several amino acids, the very building blocks of proteins. It was a landmark discovery that proved the fundamental ingredients of life could form naturally from simple chemistry. But creating the letters of the alphabet is a far cry from writing a novel, let alone having that novel begin to read and copy itself. Subsequent experiments have created even more of life's building blocks, but the leap to a self-sustaining, self-replicating system has remained stubbornly out of reach. The chasm between a complex chemical soup and what we would define as a living cell is immense. This brings us to the core of the philosophical divide that this puzzle creates. As biologist Adi Pross brilliantly framed it, life is chemistry but with a narrative. Chemistry is the set of rules, the narrative is the extraordinary, persistent story of replication and evolution that somehow emerged from those rules. So, which is it? Is this narrative a cosmic imperative, a story that is destined to be written and rewritten on countless worlds wherever the right chemical conditions persist? Or was it a freak accident, a 1 in a trillion quantum fluctuation that happened just once in one special place, making our universe, for all its grandeur, a silent and empty library save for one single solitary book? This puzzle is the ultimate bridge, connecting the cold, hard laws of physics and astronomy to the warm, messy, and breathtakingly complex world of biology. It forces us to confront not only where we came from, but how alone we might truly be in the vast cosmic dark. Every child who has ever played with a pair of bar magnets knows the fundamental rule of magnetism. For every North Pole, there must be a South Pole. Cut a magnet in half and you don't isolate a pole, you simply create two new magnets, each with its own north and south. This seems to be an unbreakable law of nature, a perfect symmetry where magnetic poles only ever come in inseparable pairs. But what if this everyday truth is actually a cosmic illusion? What if the universe does contain isolated magnetic poles, and our experience is just a quirk of our local environment? This brings us to our 25th cosmic puzzle, the perplexing case of the missing magnetic monopoles, the idea that a single magnetic North Pole could exist on its own without a corresponding South isn't just a fanciful thought experiment. It is a prediction that falls naturally out of some of our most successful physical theories. The great James Clerk Maxwell, in his elegant 19th century equations that unified electricity and magnetism, described a beautiful symmetry between the two forces. Yet, one asymmetry always stood out. While we have isolated positive and negative electric charges, protons and electrons that can exist perfectly happily on their own, we have no corresponding isolated magnetic charges. Maxwell's equations account for this by setting the term for magnetic charge to zero, but they don't explicitly forbid its existence. The symmetry seems to beg for its completion. This theoretical itch became far more compelling with the advent of quantum mechanics in the 20th century. In 1931, the legendary physicist Paul Dirac took on the problem. He demonstrated that if even a single magnetic monopole existed somewhere in the universe, it would elegantly explain one of the most fundamental mysteries in all of physics: why electric charge is quantized. Why does every charged particle in the universe carry a charge that is an exact integer multiple of the electron's charge? Dirac showed that the mere existence of a magnetic monopole would force electric charge to be quantized, a beautiful and profound connection. His work didn't just make monopoles plausible, it made them deeply desirable, a missing piece that would make the puzzle of the universe's laws more complete and symmetrical. Guided by this powerful theoretical motivation, scientists have been on a decades-long hunt for these elusive particles. They have used every tool at their disposal. They have built sophisticated detectors in deep underground laboratories, hoping to catch a glimpse of a monopole created in the high-energy collisions of cosmic rays striking our atmosphere. They have scoured ancient rocks and minerals, even samples from the moon, searching for telltale tracks that could only have been left by a massively heavy, highly ionizing monopole passing through. They have designed intricate experiments using superconducting loops, which, according to theory, would show a distinct and permanent jump in electrical current if a monopole ever passed through them, a phenomenon known as the Dirac veto. Despite this immense and creative effort, the result has been a resounding, uniform silence. Not a single confirmed magnetic monopole has ever been detected. So where did they all go? The most widely accepted solution to this puzzle is intertwined with another of our great cosmic mysteries: inflation. The theory suggests that monopoles aren't missing, they are simply incredibly rare. They are thought to be monstrously heavy particles, relics that could only have been created in the unimaginable energy of the universe's first fractions of a second, during a phase transition as the fundamental forces separated from their primordial unity. In a standard Big Bang scenario, these monopoles would have been produced in prodigious numbers, and their sheer density would have dramatically altered the evolution of the cosmos, perhaps even preventing galaxies from ever forming. But then, cosmic inflation happened. That brief period of hyper-exponential expansion would have stretched the very fabric of space-time so dramatically that it would have diluted the density of these primordial monopoles to virtually zero. The entire observable universe, vast as it is, might contain only a handful of them, making our chances of ever finding one infinitesimally small. Their absence isn't a failure of theory. It's actually a key piece of evidence supporting the inflationary model. However, the story may not end there. Some grand unified theories which attempt to merge the electromagnetic, weak and strong nuclear forces predict the existence of a different kind of monopole. These wouldn't be the incredibly massive relics from the earliest moments, but potentially lighter, more accessible particles that could be created in the high-energy collisions of a particle accelerator. This possibility is what drives experiments like Mo-Edl, the monopole and exotics detector at the Large Hadron Collider. Mo-Edl isn't like the LHC's other massive detectors. It's a unique array of plastic tracks and aluminum foil sheets designed to do one thing: act as a trap for these hypothetical, highly ionizing particles. If a magnetic monopole is created in a collision, it would leave a permanent, microscopic damage trail in the plastic that scientists can later etch out and examine. It's a long shot, but it represents the cutting edge of the hunt, a search for a particle that would fundamentally rewrite our understanding of force and matter. The enduring mystery of the magnetic monopole forces us to confront a profound question about the nature of reality itself. Is the duality of magnetic poles an unbreakable, fundamental law of the universe, a basic rule that simply is with no deeper explanation? Or is our experience merely a local condition, a frozen accident from the early universe that has left us in a region where monopoles are so rare they are effectively absent? The search for this solitary pole is about far more than just completing a symmetrical set. It is a direct test of our deepest theories about how the universe began and how the forces that govern it came to be. Finding one would be a discovery on par with the Higgs boson, a monumental validation of decades of theoretical work. Their continued absence, however, is a quiet but persistent reminder that nature often guards her most beautiful symmetries with the utmost care. After exploring the intricate and often crowded cosmic web of galaxies, superclusters, and mysterious attractors, we now journey into one of the universe's most startling and desolate regions, a place of profound emptiness that defies our expectations of how matter should be distributed. If the cosmos is a fertile plain dotted with the glittering cities of galaxies, then the Boots void is a continent-sized desert, a staggering spherical region of near-nothingness so vast it could swallow thousands of galaxies like our own without a trace. Stretching an almost incomprehensible 330 million light-years across, this void is not just a slightly emptier patch of space. It is one of the largest known structures in the entire observable universe, and its existence challenges the very principle that on the largest scales, the cosmos should appear roughly the same everywhere. This concept, known as the cosmological principle, is a foundational pillar of modern astronomy. It assumes a homogeneous and isotropic universe, meaning that if you were to take a cube a billion light-years on a side and place it anywhere, the average density of matter inside should be roughly the same. The Boots void is a glaring billion-light-year-sized exception to this rule, based on our understanding of how the cosmic web formed from the subtle fluctuations in the early universe. A void of this magnitude simply shouldn't exist. The initial seeds of structure were too small to grow into such an immense emptiness through gravity alone in the time available since the Big Bang. Its discovery was a profound shock, forcing cosmologists to ask whether our models of structure formation are missing a crucial ingredient, or if we are witnessing the result of a statistical fluke so rare it borders on the impossible. Within this colossal emptiness, the few galaxies that do exist are like lone outposts on an infinite prairie, isolated in a way that is deeply puzzling to astronomers. While most galaxies in the universe are gravitationally bound into groups, clusters, and superclusters, the galaxies within the Boots void are overwhelmingly isolated field galaxies. They are not just rare, they are profoundly lonely, separated from their nearest neighbors by distances that are typically 5 to 10 times greater than the gaps between galaxies in our own crowded local neighborhood. This extreme isolation raises fascinating questions about their origins and evolution. Did these galaxies form in place against all odds from the meager material available? Or were they somehow left behind as islands when a vast tide of matter mysteriously drained away billions of years ago? Their very existence in such a barren environment is a puzzle unto itself, a testament to the resilience of galactic formation under the most extreme conditions imaginable. The sheer scale of this nothingness is difficult to grasp. To put it in perspective, if our Milky Way were placed at the center of the Boots void, humanity would not have known that other galaxies even existed until the 1960s. Our telescopes would have revealed nothing but empty blackness in every direction for hundreds of millions of light years. The first glimpse of another island universe would have been a discovery for the space age, not the era of Edwin Hubble. This immense scale of emptiness is what makes the void so much more than a curiosity. It is an active area of research and debate. As one astronomer aptly described it, it's like a desert in an otherwise fertile universe. This quote captures the sense of awe and bewilderment that this structure inspires a feeling that we are looking at a place where the normal rules of cosmology simply don't apply. So how did such a void come to be? Scientists are exploring several compelling and quite dramatic theories. One possibility is that the Boots void is not entirely empty of matter, but is instead dominated by a preponderance of dark energy, which on these colossal scales could act to repel normal matter and suppress the formation of galaxies, creating an ever-expanding bubble of nothingness. Another, more radical idea involves cosmic texture, a theoretical defect in the fabric of spacetime itself. Imagine the universe cooling from its incredibly hot, dense beginning like a sheet of metal. As it cools, imperfections can form wrinkles and folds in the very geometry of reality. A cosmic texture knot, as it unraveled, could have unleashed a tremendous amount of energy that literally pushed matter out of a huge region of space, leaving behind the void we see today. Then there is the possibility, humbling in its simplicity, that the Boots void is just a statistical fluke. In an infinite or near-infinite universe, even the most wildly improbable structures must appear somewhere. Perhaps we are just the unlucky observers who happen to live next door to one of the universe's grandest nothingnesses. The mystery of the Boots void forces us to confront the limits of our knowledge and the true nature of the cosmos. Is this vast emptiness a sign that our understanding of the initial conditions of the universe is flawed, that the seeds of structure were planted in a way we have not yet comprehended? Or does it hint at the action of unknown forces, perhaps related to dark energy or even more exotic physics, that operate on scales so large we are only just beginning to perceive them? This puzzle shows us that the universe is not only defined by the brilliant fires of stars and galaxies, but also by the immense, silent spaces between them. These cosmic deserts are not mere blanks on the map. They are active participants in the evolution of the cosmos, and understanding their origin is key to understanding the full, rich, and surprisingly empty story of everything. We have journeyed through the puzzles of what exists and how it behaves, but now we confront perhaps the most fundamental question of all. What was the first cause? What or who lit the fuse for the Big Bang? It is a question that seems as natural as asking what happened before you were born, but in the realm of cosmology, it is a query that may be fundamentally flawed. A trick of language and perception that pushes up against the very limits of what is knowable. We instinctively want to know what came before the beginning, but this assumes that before is a concept that has any meaning when applied to the birth of spacetime itself. If time itself began with the Big Bang, then the phrase before the Big Bang becomes a grammatical contradiction, a nonsensical arrangement of words like a married bachelor or a square circle. As Stephen Hawking so brilliantly illustrated, asking what came before the Big Bang is like asking what is north of the North Pole. You can travel north until you reach the pole, but once you are there, the very concept of north loses all meaning. The pole is the ultimate northern point. In the same way, the Big Bang may be the ultimate temporal point. There is no before because there was no time for a before to exist in. This hasn't stopped physicists from trying to peer beyond that veil, using the tools of mathematics and imagination to conceive of models where our universe is not a singular, isolated creation event, but part of a much larger and potentially eternal meta-reality. One of the most compelling of these visions is the cyclic model, a grand and ancient idea reborn with modern physics. In this view, the universe has no true beginning or end, but is engaged in an endless cosmic dance of death and rebirth. The current expansion, driven by dark energy, would continue for trillions of years until every particle is pulled apart in a big rip, or the universe becomes a cold, dilute void. But then, through a mechanism provided by string theory or other quantum gravitational effects, this vast emptiness would somehow trigger a new Big Bang, a new hot, dense state that begins the cycle all over again. In this model, the Big Bang was not the absolute beginning, but simply the most recent turning of the page, the latest bounce in an infinite series of universes. Our entire cosmic history, from the first stars to the last black hole, is but one chapter in an eternal story with no first sentence. Another profound idea emerges from the bizarre rules of quantum mechanics, which tell us that even a perfect vacuum is not truly empty. At the tiniest scales, it is a seething, bubbling foam of virtual particles popping in and out of existence on borrowed energy. This quantum froth suggests that absolute nothingness might be inherently unstable. Some theories propose that our entire universe could be the product of a random, monumental quantum fluctuation in a primordial void, a single, incredibly unlikely bubble of false vacuum that underwent a hyper-inflationary expansion, freezing that fluctuation into the reality we now inhabit. In this scenario, the universe truly did come from nothing, but nothing in the quantum sense is a roiling sea of potentiality, not a bland and static void. This gets us closer to an answer, but it immediately begs the next question. What were the laws of physics that governed that primordial quantum realm, and where did they come from? This line of thinking naturally leads us to the most expansive and mind-bending possibility of all, the multiverse. If eternal inflation is correct, as we discussed earlier, then our Big Bang was not a unique event. It was merely one bubble nucleating in an eternally inflating background spacetime. Beyond our cosmic horizon, an infinite number of other universes are constantly bubbling into existence, each with its own unique set of physical constants and laws. Some might be stillborn, collapsing instantly upon formation. Others might be vast, empty expanses where matter never coalesced, and a precious few, like ours, might have just the right rules to allow for galaxies, stars, planets, and life. In this breathtaking vista, the question of what happened before our Big Bang is answered by the fact that there was no single before. There is only the eternal, inflationary landscape, and our universe is just one tree in an infinite forest with no first seed to be found. Each of these theories offers a way to circumvent the problem of an absolute beginning, suggesting a cosmos that is in some form eternal. But do they truly solve the puzzle, or do they just push it back a step? A cyclic universe might not have a beginning in time, but what is the source of the eternal cycle itself? A quantum fluctuation requires a quantum field to fluctuate in. Where did that field and its rules come from? A multiverse requires an eternally inflating state. What is the origin of that state and the laws that govern it? We are ultimately faced with a choice between two profoundly difficult ideas. Either the universe had an absolute beginning, a moment before which there was literally nothing, which is a concept that defies all human intuition, or the universe is eternal, which is equally baffling to contemplate. This puzzle does not just stretch the limits of human comprehension, it defines them. It forces us to confront the possibility that some questions, framed in the language of cause and effect within time, may simply be unanswerable, and that the ultimate nature of reality might forever lie just beyond the grasp of our finite mind. For all its breathtaking power to describe the cosmos, from the bending of starlight to the orbit of planets, Einstein's general relativity is, in a sense, a theory of the very large. It paints a beautiful, continuous picture of spacetime as a smooth fabric, warped by mass and energy. Meanwhile, the quantum mechanics that governs the world of atoms and particles is a theory of the very small, a realm of frantic probability, discrete packets of energy, and fundamental uncertainty. Individually, these two pillars of modern physics are stunningly successful, each validated by countless experiments and observations. But together, they are like two brilliant artists trying to paint on the same canvas using completely different languages and rules. They are fundamentally, mathematically incompatible. This great schism in our understanding of reality is the 28th puzzle, the quest for a theory of quantum gravity, and it represents the single most profound challenge in all of modern physics. The core of the conflict lies in their treatment of space and time. In general relativity, space-time is the dynamic stage upon which the drama of the universe plays out. It can curve and ripple, but it is fundamentally smooth and continuous. Quantum mechanics, however, tells us that everything else in the universe is granular. Energy, momentum, and angular momentum come in discrete, quantized packets. So, why should the stage itself be an exception? When we try to apply the quantum rules to the gravitational field, the mathematics breaks down into a storm of nonsensical infinities. It's like trying to describe the gentle slope of a sand dune by precisely tracking the position of every single grain of sand. The calculations become impossibly complex and ultimately collapse. This isn't just an academic problem. It becomes critically important in environments where both immense gravity and tiny quantum scales are forced to meet. The central singularity of a black hole, or the very first moment of the Big Bang. To understand these ultimate frontiers, we need a theory that can speak both languages fluently. The most famous and ambitious attempt at this unification is string theory. It makes a breathtaking proposition. The fundamental constituents of the universe are not zero-dimensional points, but unimaginably tiny, vibrating one-dimensional strings. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, these cosmic strings vibrate in different modes to manifest as different fundamental particles. An electron is a string vibrating one way. A quark is that same string vibrating another way. Most importantly, one of these vibrational patterns perfectly describes the graviton, the hypothetical quantum particle that would carry the gravitational force. In this elegant framework, gravity isn't a separate, troublesome force. It emerges naturally from the music of the strings. The theory also requires extra dimensions of space, 10 or more, curled up into shapes too small for us to perceive, which determine the possible vibrational notes and thus the laws of physics in our universe. It's a breathtakingly beautiful and comprehensive vision, a potential theory of everything. However, its critics point out a significant drawback. After decades of work, string theory has yet to make a single testable prediction that can be verified by experiment. It remains a magnificent mathematical castle, but one that is currently untouchable by empirical evidence. A very different path is taken by loop quantum gravity. If string theory changes the actors on the stage, loop quantum gravity changes the stage itself. It proposes that space is not smooth and continuous, but is actually woven from a fabric of tiny, finite loops, a network of intersecting threads of gravitational field. Think of it like a digital photograph. If you zoom in far enough on a smooth image, you eventually see the individual pixels. Loop quantum gravity suggests that space-time itself has pixels, a smallest possible unit of volume. This granularity prevents the formation of the infinitesimal points that cause the mathematical infinities in other theories. In this view, the center of a black hole might not be a singularity of infinite density, but a transition to a new region of spacetime, and the Big Bang might not be a true beginning, but a big bounce from a previous universe that collapsed. It's a less grandiose theory than string theory, focusing solely on quantizing gravity without trying to unify all forces at once, but it too struggles with the same fundamental challenge, a lack of experimental confirmation. Beyond these two giants, other intriguing ideas are percolating. Causal dynamical triangulations uses complex computer simulations to build spacetime from simple geometric building blocks, literally growing a universe in a computer to see if quantum gravity properties emerge naturally. Some physicists are exploring the holographic principle, which suggests that all the information describing a three-dimensional volume of space, including the objects within it, might actually be encoded on its two-dimensional boundary, much like a hologram. This radical idea could solve the black hole information paradox and profoundly change our understanding of reality's fundamental structure. This decades-long quest forces us to confront a deeply philosophical question. Are we searching for a single, elegant theory of everything that will one day be discovered, completing physics and providing a final answer? Or are we discovering that reality is inherently dual, that the cosmic and the quantum are two different, equally valid perspectives that can never be fully merged into a single narrative, much like how light can be understood as both a particle and a wave depending on how you look at it? The pursuit of quantum gravity is more than a technical problem. It is a journey to the very edge of what is knowable, a testament to our insatiable drive to find a coherent story for a universe that constantly defies our intuition. The answer, if it ever comes, will not just change textbooks, it will fundamentally reshape our understanding of what it means to exist within space and time. Our current model of the cosmos, known as the Lambda CM model, has been remarkably successful at describing the universe on the grandest scales. It tells a story of a cosmos dominated by dark energy and dark matter, with the familiar stuff of stars and planets making up only a tiny fraction of the whole. To test this model, scientists create incredibly sophisticated computer simulations that let them watch this cosmic drama play out over billions of virtual years. They start with the conditions of the early universe, seed it with dark matter, and let the irresistible pull of gravity do its work, forming a vast cosmic web of filaments and halos. When they simulate the formation of a galaxy like our own Milky Way, they see something very specific. The gravitational pull of the galaxy's main dark matter halo should have captured hundreds of smaller satellite halos, each one massive enough to host its own tiny, orbiting dwarf galaxy. The simulation predicts a bustling celestial metropolis with a vast entourage of dwarf galaxy satellites surrounding the grand spiral. But when we actually look up at the sky and count these satellites, the reality is strikingly different. Instead of the predicted hundreds of dwarf galaxies circling our Milky Way, we've only found about 6 dozen. This glaring mismatch between the theoretical prediction and the observational census is known as the missing satellites problem, and it has been a persistent thorn in the side of cosmology for decades. It's as if we built a detailed model predicting a major city would have hundreds of suburbs, but when we went to visit, we only found a few dozen small towns. The model seems sound, so where is everyone? This isn't just a small accounting error. It's a discrepancy that forces us to question whether we truly understand the nature of the dark matter that makes up the vast majority of matter in the universe, or if our inventory of the cosmic neighborhood is simply incomplete. Scientists have pursued two main avenues to solve this puzzle. The first possibility is that our understanding of dark matter itself is flawed. The standard model assumes a type of dark matter called cold dark matter, where the particles are slow-moving and only interact with each other and normal matter through gravity. This simplicity is what makes the model so elegant, but it might also be its downfall. What if dark matter is slightly more complex? Theories involving warm dark matter propose particles that are lighter and faster moving. These particles would have less gravitational clumpiness, preventing the formation of the very smallest dark matter halos. In this scenario, the hundreds of tiny halos never formed in the first place, so there's nothing missing to find. The simulation was just wrong about how many small halos should exist. Other models suggest dark matter might have some internal interactions, a property known as self-interacting dark matter. This would allow dark matter particles to bounce off each other, effectively smoothing out the centers of halos and potentially making it harder for small galaxies to form and survive within them. Both of these ideas would require a significant revision to our standard model, but they remain compelling candidates to explain the satellite shortage. The second, and perhaps more optimistic, explanation is that the satellites aren't missing at all, they're just hiding. The smallest, faintest dwarf galaxies would be incredibly difficult to detect. They would contain very few stars swimming in a vast sea of dark matter, making them extremely dim and diffuse against the blackness of space. It's entirely possible that our current telescopes have only seen the tip of the iceberg, the largest and brightest of the dwarf galaxy population, and that a vast number of ultra-faint dwarfs are lurking just beyond our current detection limits, waiting to be discovered. This is where a new generation of astronomical tools comes in. The Vera-C Rubin Observatory, with its immense 3.2 billion pixel camera, is about to begin the legacy survey of space and time, a 10-year project that will repeatedly map the entire visible southern sky with unprecedented depth. This monumental effort is expected to discover dozens, if not hundreds, of these previously invisible ultra-faint dwarf galaxies, potentially solving the missing satellites problem by finally completing the census. However, even if the Rubin Observatory finds a new trove of tiny galaxies, the problem may not be fully resolved. The key will be in the numbers and the properties of these newly discovered satellites. If we find enough to match the simulations, the case could be closed. But if we still fall short, or if the new dwarfs are distributed in a way that doesn't align with the dark matter halos in the simulations, it will be powerful evidence that the issue isn't with our eyesight, but with our theory. The missing satellites problem, therefore, sits at a fascinating crossroads. It forces us to ask a critical question that gets to the very heart of modern cosmology. Is the problem with the dark matter itself, or is it simply that the universe is better at hiding its smallest galaxies than we ever imagined? The answer will either validate our core understanding of the universe's hidden architecture or send us back to the drawing board to conceive of a new, darker form of matter. Now we arrive at a puzzle so fundamental it threatened to unravel the entire Big Bang theory before a radical solution was proposed. It's called the Horizon Problem, and it asks a deceptively simple question. How did the universe get its thermostat so perfectly, uniformly set? When we look at the cosmic microwave background, the oldest light in the universe, we see that it is almost perfectly smooth. Its temperature is a nearly uniform 2.725 Kelvin everywhere we look, with only tiny 1 part in 100,000 variations. This seems unremarkable until you consider the sheer size of the observable universe and the unbreakable speed limit set by light itself. To understand the problem, imagine two people standing at opposite ends of a vast, dark plane, too wide for a shout to ever carry between them. If you see them both suddenly light a match at the exact same moment, your first assumption would be that they must have coordinated it somehow. They must have communicated to act in unison. But in the early universe, according to the standard Big Bang model, such coordination would have been utterly impossible. The cosmos expanded and cooled at a stately, predictable pace. When the CMB photons were first set free, the universe was already enormous. 2 points on opposite sides of the sky today were so far apart that light, traveling at the universe's ultimate speed limit, would not have had nearly enough time to journey between them. Those regions were causally disconnected. No information, no heat, no influence of any kind could have ever passed between them to synchronize their conditions. They were like 2 isolated islands in a vast ocean, with no boats or radios to communicate. And yet, against all odds, both islands decided to have exactly the same temperature down to a minuscule fraction of a degree. How could this be? It would be like 2 chefs in separate, soundproof kitchens with no prior communication, preparing an identical complex recipe at precisely the same time, down to the grain of salt. This profound paradox demanded a radical solution, and it was provided by physicist Alan Guth in 1980 with the theory of cosmic inflation. Inflation proposes that the universe didn't just expand, it exploded into being. For a sliver of time so infinitesimally small, it is almost impossible to conceive. From 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe underwent a period of hyper-exponential expansion, inflating by a factor of at least 10 to the 78 in volume. This wasn't like a balloon being blown up. It was like a subatomic speck of dust expanding to become larger than our entire observable universe in less time than it takes light to cross a proton. This incredible growth spurt provides the elegant solution. It tells us that the entire observable universe we see today was before inflation, a tiny, tiny patch of space that was smaller than the smallest subatomic particle. This entire region was once intimately connected, a single, causally connected neighborhood where everything could easily communicate and settle into a uniform temperature. Inflation then took this tiny, smooth, uniform patch and stretched it to cosmic proportions, preserving that uniformity across the vast expanse we see today. The horizon problem was solved. As one cosmologist perfectly summarized, the universe's uniformity is a clue to its origins, a frozen fossil pointing directly back to this incredible period of hypergrowth. Yet, while inflation is a breathtakingly elegant solution that also explains other cosmic puzzles, it remains a theory in need of direct confirmation. We see the compelling evidence of its effects, like the specific pattern of fluctuations in the CMB, but the engine that drove it, a hypothetical field called the inflaton, is completely unknown. We don't know what triggered inflation, what kept it going for that brief moment, or what made it suddenly stop and convert its immense energy into the matter and radiation that filled the nascent cosmos. This lack of a smoking gun has led some scientists to explore alternative, even more mind-bending ideas. Could the speed of light itself have been different in the early universe? The variable speed of light theory suggests that light traveled much, much faster in the first moments, allowing it to zip across the entire cosmos and synchronize temperatures before slowing down to its current constant value. It's a radical proposition that challenges one of physics' most sacred constants, but it shows the lengths to which physicists will go to solve this deep mystery. Another possibility pushes the boundaries of causality itself. Perhaps the distant regions of the universe were connected not by signals traveling through space, but by a deeper, pre-geometric connection that existed before space and time as we know them even formed. In some quantum gravity models, the concept of locality breaks down at the most fundamental level, suggesting that what we perceive as separate points could be entangled or connected in a way that transcends distance. This leads us to a profound and unsettling question. Was the early universe connected in a way we simply don't understand, a way that makes our classical notions of cause and effect incomplete? The horizon problem, therefore, is more than just a technical issue in cosmology. It is a direct challenge to our understanding of the universe's initial conditions. It forces us to confront the fact that the cosmos we see is impossibly perfectly balanced, fine-tuned in its uniformity, in a way that either requires a mechanism like inflation or points toward a revolutionary new physics that operates at the very dawn of time. Even our most pristine cosmic map, the cosmic microwave background, is not without its blemishes, quirks that defy easy explanation and hint at a universe even stranger than we've imagined. Among these, one anomaly stands out for its sheer size and stubborn refusal to be explained away: a vast, perplexingly cold region in the southern constellation of Eridanus. This isn't just a slightly cooler patch. It's a colossal anomaly, a cosmic cold spot stretching over 1 billion light-years across, where the temperature of the primordial radiation dips significantly lower than our standard models of the universe's infancy can account for. It's a feature that should not, by all rights, be there, a ghostly chill on the face of the newborn cosmos that has cosmologists scrambling for an answer. The most straightforward explanation, and the one scientists reached for first, involves the journey that the ancient CMB photons take to reach us, according to a well-understood phenomenon known as the integrated Sachs-Wolf effect. When light travels through an immense region of space that is mostly empty, a cosmic supervoid, it can behave in a counterintuitive way. As a photon enters such a void, it must climb out of the gravitational well of the dense matter that surrounds it. This costs it energy, stretching its wavelength and making it slightly redder and cooler. But as the photon travels through the expanding void itself, the universe continues to expand, and the gravitational potential of the void actually changes while the photon is in transit. In a universe dominated by dark energy, this results in the photon gaining a tiny bit of energy, making it slightly bluer and hotter. However, in the largest voids, the first effect can win out, and the photon can emerge with a net loss of energy, appearing cooler to our telescopes. This seemed like the perfect solution. The cold spot could simply be caused by the CMB light passing through a truly enormous supervoid on its way to us. There was just one problem. When astronomers went looking for this proposed void, they couldn't find it. They meticulously mapped the distribution of galaxies in the direction of the cold spot, and while they did find evidence of a large underdense region, a significant void, it was nowhere near large enough or empty enough to account for the dramatic temperature drop observed in the CMB. The void we see is substantial, but the void we need to explain the cold spot would have to be of such a staggering scale and emptiness that it would be a profound anomaly in itself, challenging our models of how structure forms in the universe. The observed void is like a small pothole, but the explanation requires a canyon of continental proportions. This mismatch between the predicted cause and the observed reality has left the cold spot mystery wide open, forcing physicists to consider far more exotic and thrilling possibilities. One of the most dramatic ideas is that the cold spot is a bruise on our universe, a fossil imprint from a colossal collision with another universe in the vast multiverse. In the framework of eternal inflation, where our universe is just one bubble in a frothing meta-universe, such collisions are not just possible, they might be inevitable. If a neighboring bubble universe had bumped into ours long ago, the energy released at the boundary of that collision could have left a distinct circular signature on the CMB, a spot that would appear anomalously cold or hot. The Eridanus cold spot has a roughly circular profile, making it a compelling candidate for such a cosmic crash. It would be the first empirical evidence not just for the multiverse, but for a specific type of multiverse where such interactions can occur, a truly breathtaking possibility that would forever change our cosmic address. Another fascinating, though highly speculative, theory points to a defect in the very fabric of spacetime itself, known as a cosmic texture. Imagine the early universe cooling from its initial, unimaginably hot state. As it cooled, the fundamental fields that permeate all of reality underwent phase transitions, much like water freezing into ice. Most of the time, this freezing happens smoothly. But occasionally, knots can form in the field's twists and tangles that contain an immense amount of trapped energy. If one of these knots, a cosmic texture, were to unravel and decay in the early universe, it would release a tremendous burst of energy that would ripple outward, creating a powerful gravitational shockwave. This shockwave would then leave its imprint on the CMB in the form of a specific hot and cold pattern, a signature that some researchers argue is a good match for what we see in the Eridanus region. It would be a one-time event, a snap of the cosmic fabric billions of years ago, whose echo we are only now detecting. So, are we looking at a signpost to another reality, or the death throes of a knot in space-time? The cold spot refuses to yield its secret easily. It stands as a powerful reminder that even our most trusted map of the cosmos, the CMB, still contains areas marked "Here be dragons." It challenges us to consider that the largest structures in the universe might be governed by physics we have not yet dreamed of, and that the answers to our biggest questions may be written not in the hot, dense seeds of galaxies, but in the inexplicable, cold silences between them. Of all the fundamental concepts we take for granted, time is perhaps the most familiar and yet the most deeply mysterious. We feel its passage in the aging of our bodies, the changing of the seasons, and the relentless ticking of a clock. It has a clear and undeniable direction. We remember the past, but not the future. We can break an egg, but we cannot unbreak it. This one-way street of existence is known as the arrow of time, and its existence is a profound puzzle because the fundamental laws of physics that govern our universe don't seem to care about this direction at all. If you were to take a film of two billiard balls colliding and then run that film backwards, the motion would look just as valid and obey the same laws of physics. The equations of Newton, Einstein, and even quantum mechanics are almost perfectly time-symmetric. They work just as well running forwards as they do backwards. So why does our macroscopic experience of reality have such a powerful, irreversible forward momentum? The most compelling answer science has found lies in a concept from thermodynamics: entropy. Entropy is a measure of disorder, of the number of ways a system's components can be rearranged without changing its overall appearance. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. It can only stay the same or increase. In other words, the universe has an inbuilt tendency to move from order to disorder. This is why an egg can scramble but never unscramble, why ice melts in a warm room but never spontaneously refreezes, and why perfume disperses throughout a room but never gathers back into the bottle. The increase of entropy provides a powerful statistical arrow of time. There are simply far more ways for things to be messy and disordered than there are for them to be neat and ordered, so over time, systems naturally tend toward the more probable high-entropy states. But this brilliant explanation only pushes the mystery one step further back in time. If the arrow of time is defined by the increase of entropy, then we must ask, why was the entropy of the early universe so incredibly low? The Big Bang presents us with a universe that was, by all accounts, in a state of exquisite order, a hot, dense, and remarkably smooth soup of particles. This was a state of extremely low entropy, a highly improbable starting point that has been winding down and becoming more disordered ever since. The real puzzle of time's arrow, then, is not why entropy increases now, but why it was ever so low to begin with. We are like a detective who finds a shattered vase and understands that it fell, but is completely baffled as to why the vase was ever perched so precariously on the mantelpiece in the first place. The initial condition of our cosmos seems to be a special, fine-tuned boundary that sets the entire temporal narrative in motion. Physicists have proposed several profound ideas to explain this low entropy past. The most straightforward is simply to accept it as a brute fact, an axiom known as the past hypothesis. This theory postulates that the universe began in a state of low entropy, and that's that. It's the ultimate initial condition, a law in itself that we must just accept. While logically consistent, this answer feels deeply unsatisfying to many, as it doesn't provide any deeper mechanism or reason for why the cosmos started this way. A more ambitious theory connects the arrow of time to the expansion of the universe itself and the mysterious nature of gravity. Gravity is the great organizer. It takes a smooth, low-entropy distribution of matter and gas and clumps it into high-entropy structures like stars, galaxies, and black holes. The tremendous gravitational pull of a black hole, in particular, creates a region of such incredibly high entropy that it may account for the vast majority of the disorder increase in the universe. In this view, the arrow of time is set by the cosmic expansion, creating the potential for gravity to work its clumping magic, driving the overall increase of entropy. This leads us into even deeper waters, where the nature of time itself may be questioned. Could the flow of time be an emergent property, an illusion that arises from the complex correlations between quantum particles? In some interpretations of quantum mechanics, the perception of a moving present moment might be a product of our consciousness interacting with a reality where all moments in time exist simultaneously in a static block universe, a concept sometimes called eternalism. The physicist Sean Carroll captured this enigmatic duality beautifully when he noted that time is what prevents everything from happening at once. This quote hints that time might be the fundamental stage, but it also playfully suggests that our experience of its flow could be a cognitive necessity rather than a physical absolute. The puzzle of time, therefore, forces a philosophical confrontation. Is the relentless forward march of time a fundamental, irreducible feature of the cosmos, woven into its very fabric? Or is it a grand illusion, a story we tell ourselves to make sense of a reality where the past, present, and future are equally real, and our journey from one to the next is merely a trick of the light? Imagine a cosmic carousel, a vast spiral galaxy like our own Milky Way, spinning gracefully in the void. Each star is like a child on that carousel, held in its circular path by the gravitational pull of all the other stars, gas, and dust making up the ride. Now think about how a carousel works. The horses on the outside have to move much faster to keep up with those near the center, covering a greater distance in the same amount of time. You would expect the same to be true in a galaxy. The stars orbiting far out in the galactic suburbs, where the visible mass is sparse, should be moving much more slowly than those whizzing around the dense, bright core. This isn't just an expectation, it's a direct prediction of Newton's law of universal gravitation, the same law that has perfectly described the orbits of planets in our solar system for centuries. But in the 1970s, astronomers like Vera Rubin, using painstaking observations, discovered something that defied this basic logic. They measured the orbital speeds of stars and clouds of hydrogen gas at various distances from the centers of spiral galaxies, plotting what became known as rotation curves. The results were astonishing. Instead of those distant stars slowing down as expected, their orbital speeds remained high, often flatlining out to the very edges of the galaxy where the light from stars all but disappears. These stars were moving so fast that the gravity from all the visible matter in the galaxy, every star, every nebula, every planet, was utterly insufficient to hold them in orbit. According to the known laws of physics, these stars should have been flung off into intergalactic space, like a child on an out-of-control carousel being thrown clear across the fairground. The galaxies, by all rights, should have been flying apart, yet they weren't. Something invisible and immensely powerful was holding them together. This was the galaxy rotation problem, and it presented a stark choice. Either our understanding of gravity, which had been proven correct everywhere else we'd ever looked, was fundamentally wrong on the scale of galaxies, or there was a tremendous amount of matter in the galaxy that we could not see. The scientific community, after much debate, largely embraced the latter explanation, giving birth to the dark matter hypothesis. This invisible substance, whatever it is, would form a massive, spherical halo around the visible disk of the galaxy, its gravity providing the extra pull needed to keep those high-speed outer stars on their path. The rotation curve, that flat line tracing the unexpectedly constant speed of stars, became the first and most powerful piece of evidence for dark matter's existence, a ghostly signature written in the motion of stars. However, a small but persistent group of physicists has continued to explore the other possibility, that we are not missing matter, but that we are misunderstanding gravity. Their alternative is known as modified Newtonian dynamics, or MUND. Proposed by physicist Mordechai Milgrom in the 1980s, MUND suggests that Newton's laws of gravity behave differently at the extremely low accelerations experienced in the outskirts of galaxies. In this view, gravity doesn't fade away with the square of the distance as expected. It gets a tiny bit stronger, providing the extra tug needed to explain the star's motion without invoking any unseen matter. It's an elegant idea in its simplicity, and it does a remarkably good job of fitting the rotation curves of many galaxies without dark matter, but MUND faces its own formidable challenges. While it can explain the rotation of individual galaxies, it struggles to account for all the other evidence for dark matter that has piled up over the decades. It has a difficult time explaining the observed behavior of colliding galaxy clusters, like the famous Bullet cluster, where the gravitational lensing effect shows that the mass of the cluster is clearly separated from the visible matter. It also has a hard time fitting into the overall framework of cosmology that so successfully describes the large-scale structure of the universe and the patterns in the cosmic microwave background. For MUND to work as a complete theory, it would need to be reconciled with all this other data, a task that has so far proven immensely difficult. The debate between these two ideas is a beautiful example of how science operates at the frontier. Do we change the laws of physics, the rules of the game, to explain what we see? Or do we posit the existence of an entirely new form of matter that dominates the cosmos yet remains forever hidden from our view? This puzzle, first revealed by the strangely swift dance of stars, remains one of the most critical in all of modern science, forcing us to question the very nature of gravity and the composition of reality itself. Deep beneath the Black Hills of South Dakota, in the hushed darkness of a converted gold mine, one of the most daring and perplexing experiments in the history of science was quietly failing. Its creator, chemist Ray Davis, had designed a colossal tank filled with 615 tons of a common industrial cleaning fluid, perchloroethylene. His goal was audacious: to catch ghosts. More specifically, he was trying to catch neutrinos, the ethereal, almost massless particles that stream out from the heart of the sun by the trillions every second, born from the nuclear fusion reactions that power our star. According to our best models of solar physics, Davis's tank should have been capturing about 1 neutrino every single day. These ghostly particles would interact with the chlorine in the fluid, transmuting it into a radioactive form of argon that Davis could then painstakingly count atom by atom. But after years of meticulous, frustrating work, the results were in, and they made no sense at all. The tank was almost empty. Davis was detecting only about 1 neutrino every 3 days. A full 2/3 of the solar neutrinos that our theories insisted must be there were simply missing. This was the solar neutrino problem, and for decades it was a quiet crisis that threatened to undermine our understanding of both the sun and the fundamental laws of particle physics. The implications were terrifying. There were 2 potential culprits, and both pointed to a profound error in our knowledge. Either we were wrong about how the sun works, or we were wrong about the fundamental nature of neutrinos. The first possibility was deeply unsettling. Our entire model of stellar evolution, the brilliant edifice built by decades of astrophysics, predicted a specific number of electron neutrinos flowing from the sun's core. If that number was wrong, it could mean we didn't truly understand the engine that has sustained life on Earth for billions of years. Perhaps the sun's core was cooler than we thought, or its nuclear reactions had temporarily paused, sending it into a silent crisis that would eventually see it flicker and fade. The alternative was equally radical. Perhaps the neutrinos themselves were fooling us. The standard model of particle physics, which has been spectacularly successful at describing the subatomic world, held that neutrinos were massless, ghostly travelers that moved at the speed of light and came in 3 immutable flavors: electron, muon, and tau. Davis's experiment could only detect electron neutrinos. What if the neutrinos weren't missing, but were changing their identity on the long journey from the sun's core to our planet? The answer, when it finally came, was a stunning validation of human curiosity and a dramatic overthrow of established dogma. It wasn't the sun that was wrong, it was our picture of the neutrino that was incomplete. The solution was a bizarre quantum phenomenon known as neutrino oscillation. The theory proposed that the 3 flavors of neutrino are not fixed and separate, but can morph into one another as they travel through space. An electron neutrino born in the sun could, by the time it reaches Earth, have transformed into a muon or tau neutrino, invisible to Davis's chlorine detector. But for this metamorphosis to be possible, neutrinos could not be massless as the standard model demanded. They had to have a tiny but non-zero mass. Different masses would cause the quantum waves of the different neutrino states to fall out of sync, leading to this constant probabilistic identity shift. This was heresy. It required physics beyond the standard model, a crack in a seemingly perfect foundation. Proof required a new kind of experiment, one that could detect all 3 flavors of neutrinos. This came from magnificent observatories like Super Kamiok and in Japan, and the Sudbury Neutrino Observatory in Canada. SNO, in particular, was a masterstroke of design. Using 1,000 tons of heavy water where the hydrogen is replaced by deuterium, it could measure the total flux of all neutrino flavors coming from the sun, as well as the flux of just electron neutrinos. Its results, published in 2001, were definitive and breathtaking. The total number of neutrinos arriving from the sun matched the solar model's prediction almost perfectly. The missing 2/3 hadn't been missing at all. They had simply been in disguise, having oscillated into flavors Davis couldn't see. Ray Davis, who had endured years of skepticism, was finally vindicated, sharing the Nobel Prize in Physics in 2002 for his pioneering work. His humble reflection captured the moment perfectly. We had to accept that neutrinos are stranger than we thought. This discovery did far more than just solve a puzzle. It flung open an entirely new window on the universe. It gave birth to the field of neutrino astronomy. We now know that these shape-shifting phantoms are not just solar messengers. They are cosmic informants carrying news from the most violent events in the cosmos: supernova explosions, merging neutron stars, and the raging hearts of active galaxies. Because they interact with matter so weakly, they travel in straight lines from their source, unaffected by magnetic fields, delivering pristine information about the cataclysms that created them. The detection of 24 neutrinos from supernova 1987A, hours before its light reached Earth, was a triumphant proof of this new astronomy. The solar neutrino problem, a decades-long mystery born in a South Dakota mine, ultimately revealed that some of the universe's deepest secrets are carried by its most elusive particles, forcing us to rewrite the textbooks and forever changing our place in the cosmos. But this elegant and self-consistent timeline, this grand story of our cosmos from a fiery birth to its current expanded state, has not been without its dramatic challenges. In fact, one of the most unsettling puzzles in modern cosmology arose from a seemingly simple contradiction. Some of the universe's oldest stars appeared to be significantly older than the universe itself. Imagine finding a family heirloom, an antique pocket watch, and discovering through carbon dating that it was crafted a full century before your great-grandfather was even born. That was the precise nature of the crisis that astronomers faced just a few decades ago. The most ancient stellar systems we can observe are the magnificent globular clusters, dense, spherical swarms of hundreds of thousands of stars that orbit the halo of our galaxy like distant, glittering bees. These clusters are the retirement homes of the Milky Way. Their stars are metal-poor, meaning they were forged from the pristine hydrogen and helium left over from the Big Bang, with very little contamination from the heavier elements cast off by later generations of stars. By studying the light from these ancient suns and plotting them on a Hertzsprung-Russell diagram, astronomers can pinpoint the moment when the most massive stars in the cluster exhausted their fuel and left the main sequence, effectively dating the entire cluster. Early calculations using this method often yielded ages for these clusters that pushed beyond 15, even 16 billion years. Meanwhile, estimates for the age of the universe, derived from its rate of expansion and the density of matter within it, were coming in significantly lower, around 10 to 12 billion years. The paradox was breathtaking. How could the contents of the universe be older than the universe that contained them? This glaring inconsistency was not a sign that everything was wrong, but a powerful catalyst that drove the field of cosmology toward ever greater precision. It forced a rigorous re-examination of both stellar astrophysics and our cosmic measuring tapes. On the stellar side, astronomers realized that their models of how old stars evolve and cool were incomplete. They hadn't fully accounted for subtle effects like the diffusion of helium within a star's interior, which can change its brightness and temperature over time and thus affect the age estimate. Refining these models brought the calculated ages of the oldest globular clusters down into a much more comfortable range of 12 to 13 billion years. At the same time, our measurement of the universe's expansion history was undergoing its own revolution. The deployment of space telescopes like Hubble, and later the exquisite mapping of the cosmic microwave background by WMAP and Planck, allowed us to measure the key cosmological parameters with unprecedented accuracy. We now know the universe is 13.8 billion years old, with an uncertainty of just a few tens of millions of years, a blink of an eye in cosmic terms. This age provides a perfect, comfortable window for the formation of those first globular clusters. The universe was already a few 100 million years old when the very first stars began to ignite, meaning the oldest stars we see are indeed younger than the cosmos itself. The paradox, it seemed, was solved, yet the cosmos has a way of keeping us humble. Just when we think we have a handle on the timeline, a new outlier appears. Enter HD 140283, a faint star in the constellation of Libra that has earned the dramatic nickname the Methuselah star. Spectroscopic analysis reveals that this star is incredibly metal-poor, even more so than most globular cluster stars, suggesting it is a true second-generation star, formed from material that was only lightly seasoned by the first supernova. When astronomers used its well-measured brightness, distance, and composition to estimate its age, the initial results were, once again, shockingly high. Some analyses placed its age at around 14.5 billion years, a full 700 million years older than the universe. This wasn't a crisis of an entire population of stars, but a challenge from a single, ancient individual. However, rather than overturning cosmology, this new puzzle is almost certainly a testament to the fiendish difficulty of stellar archaeology. Pinpointing the age of a single, isolated star is an incredibly complex task, riddled with potential pitfalls. The uncertainty lies in the exact distance to the star, its precise chemical composition, and the models of how those specific elements affect opacity and energy transport within its interior. A slight tweak in any of these parameters can change the age estimate by hundreds of millions of years. Subsequent, more careful studies that incorporated a better understanding of the star's oxygen content and a more precise distance measurement from the Gaia satellite have brought its estimated age down to around 13.5 billion years, comfortably within the age of the universe, though still making it one of the oldest known objects in existence. The enduring lesson of this puzzle is not that our fundamental timeline is broken, but that precision is everything in astrophysics. The age of the universe is not a number we pluck from the air. It is a carefully woven tapestry of evidence from independent sources, the expansion rate measured by distant supernova, the detailed structure of the cosmic microwave background, the abundance of light elements from Big Bang nucleosynthesis, and the ages of the oldest stars. For our standard model of cosmology to be valid, all of these threads must weave together into a consistent picture. The fact that they do, after centuries of observation and decades of theoretical refinement, is a triumph of human reason. Yet the occasional outlier, like the Methuselah star in its initial analysis, serves a vital purpose. It keeps us questioning, it keeps us measuring, and it forces us to sharpen our tools and our thinking. It begs a final, profound question. Could the universe be older than we think? While there is currently no compelling evidence to suggest it is, the history of science teaches us to remain open to the possibility that our next generation of telescopes might reveal a deeper layer of cosmic history, a faint signal from a time before we thought anything could have existed at all. This puzzle underscores that in the grand quest to understand the cosmos, the relentless pursuit of accuracy is not just a technical exercise. It is the very process by which we uncover the true story of everything. For decades, the rules of nuclear physics have seemed as solid and unshakable as the nucleus itself. We know that protons and neutrons bind together to form the incredible variety of atomic cores that make up our world, held fast by the powerful nuclear force. But this force has a strict requirement. It demands a careful balance. A nucleus needs both protons and neutrons to be stable. The interplay between them is what creates the binding glue. A clump of protons alone would fly apart due to their mutual electric repulsion, and according to every established textbook, a cluster of neutrons alone should be utterly impossible. Without protons to provide the stabilizing influence, the nuclear force simply shouldn't be able to bind neutrons to each other. even a simple dynatron, a pair of neutrons, has never been found to exist as a stable, bound entity. The very idea of a tetraneutron, a fleeting cluster of 4 neutrons, was long considered nuclear physics heresy, a theoretical fantasy dismissed by most serious physicists. That's why the physics community was sent into a spin when experimental evidence began to suggest that this impossible object might be real, if only for a sliver of time too brief to comprehend. The story began to take shape in 2002 when a team in France announced a startling result. They weren't looking for tetraneutrons, they were conducting a routine experiment, firing a beam of helium-8 nuclei at a helium-4 target. But in the debris of these collisions, they detected signals that were incredibly difficult to explain without the transient existence of a 4-neutron cluster. The results suggested that for about 10 to the power of -22 seconds, a billionth of a second, this phantom particle flickered into existence before immediately disintegrating. It was a claim so extraordinary that it was met with intense skepticism. Critics argued that what the team saw wasn't a true bound state, but merely a subtle final state interaction, a statistical illusion where 4 unbound neutrons just happened to be flying away from the collision point in a way that mimicked a brief connection. The controversy simmered for over a decade, a tantalizing maybe hanging over the field. Then, in 2016, a Japanese team at the RIKEN Research Institute conducted a more precise and controlled follow-up experiment. They used a different approach, colliding a beam of helium-8 nuclei with a liquid helium target and employing a sophisticated array of sensors to track the products with exquisite detail. Their results were even more compelling. The signatures they observed strongly supported the interpretation that a resonant tetraneutron state was indeed being formed, a quasi-stable structure that lived just long enough to be inferred from the particles it decayed into. This wasn't a stable nucleus you could put in a bottle. It was a ghost at the nuclear feast, a resonant state that challenged the very definition of what a nucleus can be. If confirmed, the implications of such a discovery would ripple through our understanding of physics on multiple levels. At its most fundamental, it would force a dramatic rewrite of the models describing the strong nuclear force. Perhaps there are unknown aspects to how neutrons interact at very short ranges, a subtle twist in the force that only reveals itself under the most extreme and fleeting conditions. It could point to the existence of a new, very weak force that only acts between multiple neutrons, a force that has remained hidden because its effects are normally swamped by the mighty strong force. Alternatively, it might not be a force at all, but a completely new type of nuclear configuration that theorists hadn't dreamed of, a state of matter where the rules are temporarily rewritten. Beyond the theoretical, the existence of tetraneutrons would have profound consequences for our understanding of the most extreme objects in the universe, neutron stars. These cosmic giants are the collapsed cores of massive stars, essentially city-sized atomic nuclei where gravity has crushed matter together so fiercely that electrons have been pushed into protons, turning the entire star into a vast sea of neutrons. The properties of this neutron-rich matter, how stiff it is, how it responds to pressure, what strange particles might form within it, are what determine the star's maximum mass and size, and whether it will collapse into a black hole. The possibility that neutrons could form these fleeting clusters, even for a moment, would introduce a new variable into the equations of state that describe this ultra-dense material. It could change our predictions for how neutron stars behave, how they cool, and even how they might ring like bells when they collide, sending gravitational waves through the fabric of spacetime. The hunt for definitive proof is now the focus of a new generation of experiments. researchers are designing more sophisticated setups, hoping to create tetraneutrons in different ways and observe their decay products with even greater precision. The goal is to move from seeing suggestive signatures to making an unambiguous, watertight detection that even the most hardened skeptic must accept. This painstaking process is a beautiful example of how science self-corrects and edges toward the truth, one careful measurement at a time. The tetraneutron controversy, therefore, is far more than an academic debate over a fleeting particle. It is a stark reminder that even in the heart of the atom, in a realm we thought we had mapped and understood, profound mysteries can still emerge, challenging our most basic assumptions and opening doors to a universe that is always more strange and wonderful than we imagine. If the cosmic microwave background is the universe's most perfect and ancient canvas, then the first and most obvious brushstroke we see upon it is not a random fluctuation, but a direct message about our own place in the cosmos. This is the puzzle of the CMB dipole anisotropy, and it begins with a simple, profound fact: we are moving. The entire solar system, our entire galaxy, is not sitting still in some absolute cosmic frame of reference. We are rushing through space at a staggering velocity, and the universe itself has provided us with the ultimate speedometer to measure our motion. When we look at the CMB, that pristine remnant of the Big Bang, we find it is not perfectly uniform. It is slightly warmer by about 3.36 millikelvin in one direction of the sky toward the constellation Leo, and slightly cooler by the same amount in the exact opposite direction. This pattern, this dipole, is the unmistakable signature of a Doppler shift, the same effect that makes a police siren sound higher pitched as it races toward you and lower as it speeds away. The photons coming from the direction we are moving toward are blue-shifted, packed a little closer together, making that region appear very slightly warmer. The photons from behind us are redshifted, stretched out, making that region appear cooler. By measuring this temperature difference, we can calculate our velocity with incredible precision. Our solar system is moving at approximately 370 kilometers per second relative to this primordial background radiation, which defines the ultimate rest frame of the universe itself. This cosmic rest frame, often called the CMB rest frame, is the closest thing we have to an absolute standard of stillness in the universe. It is defined by the reference point where the CMB would appear perfectly isotropic, with no dipole anisotropy at all. Our significant motion relative to this frame is a composite of many different movements: the Earth spinning on its axis, the Earth orbiting the Sun orbiting the center of the Milky Way galaxy, and the Milky Way itself being pulled by the gravitational forces of nearby objects. The largest component of this motion comes from the gravitational pull of the immense structures surrounding us. We now understand that a significant portion of our velocity is due to the gravitational attraction of the Virgo cluster, the largest nearby cluster of galaxies, which is pulling us inward. But that is only part of the story. The rest of our motion is part of a much larger, more mysterious flow. Our entire local group of galaxies, including Andromeda and the Milky Way, is itself caught in a vast river of galaxies all moving in the same direction toward the gravitational center of the Laniakea supercluster, the great attractor region we discussed earlier. This grand cosmic flow connects the CMB dipole directly to the large-scale structure of the universe, making it a powerful probe of the distribution of mass, both seen and unseen, on the very largest scales. Yet, for all we have mapped, a puzzling discrepancy remains. When we add up all the known gravitational contributions, the pull from the Virgo cluster, the great attractor, and even the immense Shapley supercluster far beyond it, the total calculated velocity doesn't perfectly match the 370 kilometers per second we measure from the CMB dipole. There is a residual motion, a portion of our journey that seems unexplained by the catalogued masses of galaxies and clusters we can see. This is the heart of the 37th puzzle. It strongly suggests that there are still unseen masses, vast concentrations of dark matter, or perhaps even larger structures beyond the current limits of our surveys, that are exerting a gravitational pull on us and our entire local universe. As the saying goes, we are not at rest in the universe, and this simple statement carries a deep implication. Our motion is a clue, a cosmic detective story written in the subtle temperature variations of the oldest light there is. It forces us to ask what other hidden architects are out there, shaping the paths of galaxies with their invisible gravity. The CMB dipole is therefore far more than a simple speed check. It is a fundamental tool for cosmology, a way to weigh the universe and trace the hidden skeleton of dark matter that dictates the motion of everything within it. For nearly a century, we've thought of the proton as a familiar, well-understood cornerstone of matter. It sits at the heart of every atom, a positively charged ball that defines the elements and, by extension, the very substance of our physical world. We've measured it, probed it, and incorporated its properties into the very foundations of particle physics. It is, in many ways, the ultimate known quantity. Or so we thought. This confidence was shattered by a discrepancy so precise and so stubborn that it has thrown one of physics' most trusted particles into a state of profound mystery. The puzzle is this: when you measure the size of a proton's cloud of charge using two different, seemingly ironclad methods, you get two different, irreconcilable answers. It's as if you measured the same room with two different laser tape measures and found one read 10 feet across and the other read 9, a difference that should be impossible for instruments of such precision. The first method is a classic technique that has been refined over decades. It involves firing a beam of electrons at a proton target and watching how they scatter. Just as you could deduce the size and shape of a hidden object by carefully tracking the ricochets of thousands of ping-pong balls thrown at it, physicists can map the proton's charge radius from the pattern of how electrons deflect around it. This approach has given us a very consistent value over the years, establishing the proton's radius at about 0.877 femtometers. A femtometer is 1/4 of a meter, a scale so small it defies everyday comprehension, but in the subatomic world, this number was considered as reliable as a physical constant. The crisis emerged when a team of scientists decided to try a different, more precise approach. Instead of using electrons, they created an exotic form of hydrogen where the electron, which orbits the proton, was replaced by its heavier cousin, the muon. A muon is identical to an electron in every way except mass. It's over 200 times heavier. This greater mass means a muon orbits much closer to the proton, like a satellite in a tight, low orbit. This proximity makes the muon exquisitely sensitive to the proton's size. The energy levels of its orbit depend minutely on the proton's charge distribution. By using lasers to measure the precise energy required to kick the muon from one orbital level to another, a technique called laser spectroscopy, the researchers could calculate the proton's radius with an accuracy an order of magnitude greater than the electron scattering method. When they did this, the result was not a more precise confirmation of the old number. It was a shock. The radius they measured was 4% smaller, a difference of just 0.03 femtometers, but a monumental chasm in the world of precision physics. This wasn't a minor statistical blip. It was a direct contradiction that became known as the proton radius puzzle. This tiny discrepancy sends seismic waves through the heart of quantum electrodynamics, or QED, the theory that describes how light and matter interact. QED is arguably the most successful and precisely tested theory in the entire history of science. Its predictions have been verified to more than 10 decimal places. The energy levels of hydrogen calculated with QED are a benchmark of this success, but those calculations depend critically on the proton's radius. The muonic hydrogen measurement didn't just suggest the proton was smaller. It implied that if this new value was correct, then something was fundamentally wrong with our QED calculations for this exotic atom. Either our understanding of how muons interact with protons was deeply flawed, or this was the first crack in the magnificent edifice of QED, a hint of new physics operating just beyond our current perception. The most thrilling possibility is that the discrepancy is a signal of a new force or a new particle. One compelling theory proposes the existence of a dark photon. This wouldn't be the familiar photon of light, but a hypothetical particle associated with the dark sector of the universe. This dark photon could mediate a new, extremely weak force between particles. Crucially, because the effect would be so subtle, it would be completely negligible for the lightweight electron in normal hydrogen. But for the much heavier muon, orbiting so close to the proton, this new force could exert a tiny additional pull, subtly altering its energy levels and tricking us into measuring a different proton size. The proton radius puzzle, therefore, transformed from a technical measurement problem into a potential portal to an entirely new realm of physics, a world of dark forces that have been hiding in plain sight within the most common particle in the universe. In the years since, a furious effort has been underway to resolve the tension. New experiments using both electron scattering and novel methods, like measuring the Lamb shift in regular hydrogen with unprecedented accuracy, have started to close the gap. Some of the most recent results suggest a value that sits almost perfectly between the two original contenders, hinting that the truth may involve a subtle understanding of systematic errors in both methods that we are only now uncovering. Yet the puzzle is not fully solved. The community awaits independent confirmation from other exotic atom experiments, like those using muonic helium, to provide the final verdict. This process, the tension between contradictory results, the development of new experiments, and the slow, grinding progress toward consensus, is science at its most vital. It demonstrates that even the most familiar and trusted elements of our reality can still hold profound secrets, reminding us that the universe always has another card to play, another layer of mystery to reveal, if only we are precise and patient enough to look. Imagine a cosmic compass, a tiny subatomic particle spinning in the void like a perfect, invisible top. Just like a child's magnet, this spin gives it a magnetic personality, a strength and orientation that physicists call its magnetic moment. For every particle in the universe, this value can be predicted with breathtaking precision by the standard model of particle physics, the magnificent rulebook that has governed the subatomic world for decades. It is a theory of such stunning accuracy that its predictions have been verified to more than 10 decimal places. But there is one particle, the muon, that has always been a little rebellious, a little wonky. Its magnetic moment, the way its internal compass needle wiggles in a magnetic field, has never quite matched the standard model's grand prediction. The difference is almost absurdly small, a discrepancy of about 2.5 parts in a billion. Yet, in the world of ultra-high-precision physics, this tiny anomaly is not a rounding error. It is a screaming siren, a potential crack in the foundation of our understanding of the universe. The muon itself is a fascinating character. It is often called the heavy cousin of the electron, identical in every way except that it is 200 times more massive and lives for only 2 millionths of a second before decaying into lighter particles. This greater mass is the key to its rebellious nature. Because it is heavier, it can sense the quantum vacuum in a way the electron cannot. The space around us is not truly empty. It is a seething, bubbling foam of virtual particles that constantly pop in and out of existence, borrowing energy from nothing for the briefest of moments. As a muon moves through this quantum froth, these fleeting particles interact with it, subtly affecting its magnetic properties. The standard model accounts for all the known virtual particles, photons, electrons, quarks, and more, and calculates their collective influence on the muon's magnetic moment with painstaking detail. The fact that the measured value disagrees with this prediction suggests that the muon is sensing something else in the quantum foam, something the standard model doesn't include. It's as if our muon, this sensitive quantum compass, is being ever so slightly deflected by invisible, ghostly presences that our current physics cannot describe. This is why the entire physics community held its breath when the results from the Muon G2 experiment at Fermilab were announced. This magnificent machine is a feat of engineering designed for one purpose: to isolate muons and measure the precise wobble in their spin as they race around a giant, superconducting magnetic ring at nearly the speed of light. The experiment is incredibly delicate, requiring scientists to account for every possible external influence, from the Earth's own magnetic field to tiny imperfections in the ring itself. The new Fermilab data didn't just hint at the anomaly, it confirmed it with greater certainty than ever before, aligning perfectly with earlier results from a previous experiment at Brookhaven National Laboratory. The combined results show the discrepancy with the standard model now stands at a confidence level of 4.2 sigma. In the language of particle physics, this means there is only about a 1 in 40,000 chance that this is a random statistical fluke. It is a result that demands an explanation. As one physicist involved in the DISCOVERY Chinese letter stated, this could be the crack in the standard model. So what could these unseen influences be? The most thrilling possibilities point to entirely new physics. The muon's anomalous wobble could be the first direct evidence for particles that have so far existed only in theory. Prime candidates are the particles predicted by supersymmetry, an elegant concept that posits every known particle has a heavier super-partner particle. These particles, if they exist, would be popping in and out of the quantum vacuum and could easily account for the muon's strange magnetic behavior. Their discovery would be a monumental revolution, opening a vast new chapter in physics. Alternatively, the muon could be sensing the presence of dark matter particles interacting with it in ways we haven't yet imagined. Or perhaps there are entirely new forces of nature at work, forces so weak they only reveal themselves in the most precise experiments imaginable. Each possibility is more breathtaking than the last, suggesting that we are on the verge of discoveries that could completely reshape our understanding of the cosmos's fundamental building blocks. Yet, the story is not without its own intriguing tensions. While the experimentalists at Fermilab were measuring the muon's wobble, another group of physicists were performing a different kind of tour de force, a purely theoretical calculation of what the standard model prediction should be, using a method called lattice QCD that runs on the world's most powerful supercomputers. Some of these new theoretical calculations have intriguingly found a value much closer to the experimental measurement, potentially closing the gap and suggesting the anomaly might not be as severe as we thought. This has created a fascinating standoff, a high-stakes drama within the physics community. Is the discrepancy a sign of new physics, or is it a sign that we are still learning how to calculate the incredibly complex dance of quarks and gluons within the standard model itself? The answer will not come easily. It will require even more precise measurements from Fermilab and other experiments, coupled with relentless refinement of the theoretical calculations. The muon, this fleeting, heavy particle, has become the focal point of a grand inquiry, its subtle magnetic wobble holding the potential to either validate our current understanding of the universe or shatter it, revealing a reality far richer and more mysterious than we ever dreamed. At the very heart of a black hole, according to Einstein's general relativity, lies our greatest and most terrifying failure of understanding, the singularity. It is a point of infinite density where the curvature of spacetime becomes infinite and the known laws of physics simply cease to function. It's a mathematical warning sign, a glaring signal that our most brilliant theory of gravity has been pushed into a regime where it can no longer be trusted. This isn't just a scientific inconvenience, it's a direct confrontation with the unknown, a cosmic dead end where our equations break down and our imagination fails. But what if this singularity isn't the final word? What if it's not a place of infinite destruction, but merely a signpost pointing toward a deeper, more complete theory of reality? A theory that seamlessly weaves together the fabric of spacetime with the bizarre rules of the quantum world. This is the monumental challenge of the Singularity Resolution, the quest to discover what truly lies at the center of a black hole. The most promising paths forward come from the daring frontiers of theoretical physics, where scientists are attempting to construct a theory of quantum gravity. One of the most fascinating ideas emerges from string theory, a framework that proposes the fundamental building blocks of the universe are not point particles but tiny, vibrating strings. In this view, the mysterious interior of a black hole might not be a collapsing point, but a vast, tangled ball of strings, a fuzzball. Imagine the event horizon not as a gateway to a crushing singularity, but as the surface of a cosmic string star, a complex, fuzzy structure with no sharp boundary and no infinitely dense core. The fuzzball proposal is elegant because it naturally does away with the singularity. The black hole is filled with the stringy material all the way to its center, which has a high but finite density. This isn't just a mathematical trick. It could provide a direct solution to the black hole information paradox. If there is no singularity to destroy information, then all the data about what fell into the black hole could be preserved within the complex quantum state of this fuzzball, waiting to be slowly radiated back out as Hawking radiation. The information isn't lost, it's just incredibly scrambled. Another compelling vision comes from loop quantum gravity, an approach that suggests spacetime itself is not smooth and continuous, but is woven from tiny, discrete loops, a fabric with a finite, pixelated structure. This granularity of space provides a natural break on gravitational collapse. Instead of matter collapsing into an infinitely small point, it reaches a point of maximum density where the repulsive force of quantum gravity becomes overwhelming. This could cause the collapsing material to bounce, potentially spewing it back out into a new region of spacetime. In this stunning scenario, a black hole might not be a one-way street to oblivion, but a tunnel, a gateway to another universe or a different part of our own. The terrifying singularity is replaced by a cosmic trampoline, a quantum bridge connecting different realms of existence. This idea of a black hole bounce transforms the black hole from a destructive end into a transformative passage, a concept that completely rewrites the fate of anything daring enough to cross the event horizon. These theories are breathtaking in their implications, but they remain, for now, firmly in the realm of the highly theoretical. We lack the technology to peer inside a black hole, and we cannot yet create the conditions to test these ideas in a laboratory. They are beautiful mathematical constructs, stories we tell about a place we can never visit. Yet, their importance cannot be overstated. Resolving the nature of the singularity is the key to unlocking a unified theory of physics. a complete description of our universe that works from the smallest quantum fluctuation to the largest cosmic structure. It represents the absolute cutting edge of human exploration, not with telescopes or rockets, but with pure thought and the language of mathematics. It forces us to ask a question that is as profound as it is simple. Will we ever truly know what happens at the heart of a black hole? The answer will determine not just the fate of information falling into these cosmic traps, but the ultimate fate of our quest to understand the fundamental nature of reality itself. As we've journeyed through these 40 cosmic puzzles, from the ghostly pull of dark matter to the quantum enigmas haunting black holes, a profound truth emerges. These mysteries are not isolated islands of ignorance. They are interconnected threads in a single, vast tapestry of uncertainty, each one pulling on the others in ways we are only beginning to grasp. Consider how the invisible grip of dark matter doesn't just explain the rapid spin of galaxies. It also dictates the large-scale structure of the universe, which in turn influences the mysterious flow we see in the CMB dipole and the Great Attractor's pull. The hunt for dark matter particles at the Large Hadron Collider is deeply tied to the hierarchy problem and the mystery of Baryon asymmetry, as new physics beyond the standard model could solve all three at once. Similarly, the black hole information paradox is inextricably linked to the quest for quantum gravity, which itself holds the key to understanding the singularity and perhaps even the very origin of the Big Bang. These are not separate challenges, they are different doors into the same mansion of the unknown, and unlocking one could swing a dozen others open. This beautiful web of ignorance is not a sign of scientific failure, but its very engine. Each unsolved puzzle is a beacon, a destination for the next generation of explorers armed with ever more powerful tools. The James Webb Space Telescope, peering back to the first galaxies, is already challenging our models of dark matter and cosmic dawn. The Vera Rubin Observatory's relentless sky survey will undoubtedly find more interstellar visitors like Oumuamua and perhaps finally pinpoint the source of those baffling fast radio bursts. Next-generation gravitational wave detectors will listen for the echoes of cosmic inflation and the collisions of primordial black holes, potentially revealing the nature of dark matter. And deep underground, in immense particle colliders and delicate neutrino observatories, we are probing the very laws of physics, seeking the particles that could explain the muon's magnetic anomaly or the missing lithium from the Big Bang. With every answer, we don't just solve a puzzle, we refine the questions, often discovering that the solution reveals an even deeper, more fascinating layer of mystery. The horizon of our knowledge doesn't recede as we approach it, it expands, offering new vistas of wonder. This endless pursuit is what defines the human spirit. For millennia, we have looked up at the starry sky not just in search of answers, but in search of better questions. There is a profound beauty in not knowing, a humility that fuels curiosity and drives us to build bigger telescopes, more powerful computers, and more elegant theories. The greatest discoveries in science have never been final pronouncements, but invitations to explore further. The realization that the Earth revolves around the Sun led to the laws of gravity, which led to the discovery of relativity, which unveiled the expanding universe and the need for dark energy, a chain of insight that stretches across centuries, each link forged from the mystery that came before. To be a scientist or simply a curious human is to embrace this endless journey, to find joy in the questions themselves. So the next time you feel overwhelmed by the complexity of the cosmos, remember that every mystery is a gift, a promise that the universe still has secrets to share, stories to tell, and wonders to reveal to those who are patient, bold, and curious enough to keep looking up and asking what's next. We have journeyed together through a cosmos brimming with mystery, from the invisible grip of dark matter shaping colossal galaxies to the repulsive phantom of dark energy tearing the very fabric of space apart. We've stood at the edge of black holes, pondering the terrifying singularities at their hearts, and delved into the quantum realm, where particles converse across impossible distances and reality itself remains undecided until the moment we look. These 40 puzzles represent the very frontiers of human knowledge, not as monuments to our ignorance, but as beacons guiding us toward a deeper understanding. They are the unanswered questions that keep science alive and pulsating with excitement, reminding us that the universe is far stranger, more vast, and more wonderfully complex than we could have ever imagined just a century ago. It is crucial to remember that an unsolved mystery is not a failure. In fact, it is the opposite. It is the most valuable commodity in science. Every great discovery in human history began as a puzzle, an anomaly that didn't fit the established narrative. The motion of the planets that didn't align with an Earth-centered universe gave us the heliocentric model. The slight wobble in Mercury's orbit that Newtonian gravity couldn't explain paved the way for Einstein's relativity. The strange radiation emanating from the center of our galaxy led us to the supermassive black hole lurking there. Each time we solve one cosmic riddle, we don't arrive at an end point. We unlock a new set of even more profound questions, and in doing so, we often develop new technologies that transform our daily lives. The quest to understand the cosmos has given us everything from satellite communications and GPS to the World Wide Web and life-saving medical imaging technologies. The drive to explore the unknown doesn't just satisfy our curiosity, it propels our civilization forward. This spirit of inquisitive wonder was perfectly captured by the visionary writer and biochemist Isaac Asimov, who once observed, "The most exciting phrase to hear in science, the one that heralds new discoveries, is not Eureka." But that's funny. That moment of confusion, that slight deviation from the expected, is where the next revolution begins. It is an invitation to adventure, a call to look closer, think deeper, and challenge what we think we know. So we encourage you to carry this spirit of curiosity with you. Look up at the night sky and wonder about the forces at play in the great darkness. Share your own thoughts and questions in the comments below. What mystery captivated you the most? Let's continue this conversation. And if you want to join us on more expeditions to the edges of understanding, be sure to subscribe. We have only just begun to scratch the surface of the universe's secrets. Never lose that sense of awe, for the cosmos is an endless source of wonder, and the next great discovery is waiting for the